Welcome to Xamarin University. My name is Mark Smith, and today I want to walk you through diagnosing memory management issues. We're going to talk about several things. First, we're going to talk about how you can identify memory leaks in your own code. Now, it's a common misconception that GC-based applications that are garbage collected don't have memory leaks, but it turns out that that's not completely true. There are a couple of cases that we have to consider in our application, and specifically the way we write our application, to ensure that the GC system works properly. Once we've talked about the baseline cases, then we're going to dive into the platform-specific cases, and we're going to look at exactly how Xamarin iOS manages your memory and how the garbage collector in Xamarin works directly with the iOS memory management system in order to properly manage your objects. And then we're going to switch gears and we're going to do the same thing, but from the Xamarin Android perspective. So let's get started by talking about basic memory management techniques and how to identify leaks within your own code. Now, the particular things that we're going to look at in this section apply to any managed application. So it's not necessarily Xamarin specific, and it's not even mobile specific. So some of the things we're going to see here would actually apply regardless of what type of application you're building. So if it's a web app or a console-based app or a UWP app or a Xamarin app, the same sort of techniques will apply here. And to start with, I want to remind you exactly how memory is managed in your applications. So .NET and Mono use what's called a garbage collector to automatically manage your memory. When you allocate memory, the system will come along periodically and it will free that memory for you. So we don't have a devoted keyword to actually get rid of memory. The closest thing we have is the iDisposable interface that indicates that you're done with an object and assets or resources that it has should be freed from the native operating system perspective, but the memory allocation itself is always actually managed and freed by the garbage collector. And this garbage collector comes along automatically, and it scans all the different objects that your application is using, and it decides what you're still actually able to access and the things that you can't, and it throws away the things that you can't. Now, we cover all of this in great detail in our CSC370 class and CSC371 class. And so if you're a little bit hazy or fuzzy on how a garbage collector works, and specifically how the one in Mono works, then make sure that you follow up with those classes to get more specific about exactly what happens when a garbage collection occurs and how you can detect that and that sort of thing. But let's move on and let's talk about the types of memory that your application has. When the operating system starts your app, it's launching a process, just like the processes that you would see in Task Manager or Activity Monitor on the Mac. And as part of that, it's going to provide some amount of memory to the process. This memory is virtualized in some way, and every allocation request made by your process is satisfied out of this bounded memory space. When you run out of this process memory, the operating system will typically terminate your application. And in this memory, the system is going to allocate the native things that we're going to work with. So this includes all the UI controls that our application uses. So in iOS, that's going to be things like UI views and UI images and map views. And in Android, it's going to be our activities and our intents and all the UI things. And in Windows, it would be the HWinds and the COM-WinRT objects that our UWP apps consume. In a native app, we'd stop there. But in a Xamarin app or a .NET app, we also have a runtime that does memory allocations for us as well. And this runtime is going to allocate out of a subset of our process memory. So this memory is shared with the process. And so the same memory segments that we allocate native objects out of are also used for our manage object, but this is a controlled region of memory that's specifically managed by either the Mono or the .NET runtime. This is the memory that's going to be garbage collected, but as developers, we're actually concerned with the whole big picture of memory, not just the managed side, because that's going to be allocated and released by the garbage collector, but we're actually concerned with the native side and the managed side, because leaks on either one of these sides will be disastrous for our application itself. And so we want to make sure to understand holistically where our memory is coming from this process memory space. Now, some objects that we allocate actually live in both worlds. And typically where we run into trouble is when these two worlds overlap. So as you can see here, we've got some objects that actually have representations in both of these memory areas. We have a native memory representation that is the native handle to the operating system thing that we're interacting with. And then we have a managed, typically a wrapper, that wraps that object and gives us access to it from our C# code. And we've got some sort of layer that's going to provide the interaction between these two halves of the object. And so here what you can see is we have a UIKit UI image, which is the C# representation of something. And then on the native iOS side, we have a real UI image that's allocated from the iOS operating system. And then we also have an Android app activity. That again is the managed object representation of what is really a Java class of Android app activity. And these two halves interact to represent the overall object that the system is actually handing us to work with. And the reality is that these special objects have to be handled in a special way because either side can decide that the object is no longer available for use. But we can't really get rid of the object until both sides agree that we don't need it anymore. Now, it's a common assumption, as I said earlier, that memory leaks don't happen when we utilize a garbage collector. And in the strictest sense, that's possibly true. However, we have a few scenarios that can cause the garbage collector to not collect memory properly, which ultimately causes exactly the same behavior and issues that we would have with a traditional memory leak. So the first case is probably the most common, and this is where we have some sort of error in our application and we're holding on to an object. In other words, we're keeping a live reference. We don't always recognize that it's a live reference, but we've cached it somewhere. Maybe it's held in a list, maybe it's in a dictionary, something that we don't realize that we're holding on to. We're going to look at a couple of cases of that. Another case is where we use thread local values. So these are memory objects that are tied to threads that are running in our application that are specific to those threads. And the problem is often this sort of data storage is tied to the lifetime of that thread. And so we can't get rid of it until the thread itself goes away. And then finally, we have an interop case where we take an object that we allocate on the managed side and we actually pass that into the native operating system for it to interact with. And these particular objects cannot be freed until the native side releases its sort of reference or identity to that particular object. And the reason why is because it's using it, and the managed side, .NET or Mono, can't determine what the native side is going to do with it. So from the native side, it just represents a block of memory that it's going to fill in or utilize in some way. And it isn't until we actually release that the object can be collected by the garbage collector. We often call these pinned objects because they have to sit in a very specific place, and the garbage collector is unable to move them. So once it's allocated and we pass that address into the native platform, it's sort of fixed in space, and it basically is locked because obviously the native side is going to use it and it only has a pointer, so it's not aware of the garbage collector, and the garbage collector at the same time is unaware of exactly how many areas of your native code is using that object or that memory address, and so it stays pinned in its location. There are several tools that we can use to identify memory issues within our application, or even just to monitor the memory heuristics of our application. So let's start with some of the native tools first. The first one we have is Instruments. Instruments is a native iOS and macOS profiling tool, and it allows you to watch for native allocations that are occurring in your application. It's useful to use this tool to be able to see the native objects that are potentially not being released. In the same way, we have a tool on the Android side called Android Device Monitor, or sometimes just called Monitor, or sometimes called ADM. And ADM allows you to see CPU and memory statistics from the perspective of the Java virtual machine. And so neither of these tools is really aware of Mono or of our C# managed environment. They are strictly looking at the native side of the environment, but they can be useful to identify issues that are occurring on the native side. In other words, things that were potentially somehow allocated on the managed side, but the managed side is no longer aware of them, but they're still being used on the native side. And that is a memory leak in the traditional sense. It's not going to go away, and it's using up space in our memory. So both of these are useful, but only to a certain point, because they're only designed to analyze the native applications. They can only see that half of the picture that we were talking about. So they can give you a quick indication that there's a problem, but isolating it to specific sections of your managed code is really outside the bounds of what these tools can accomplish, because they don't understand the managed stack and they can really only see native code. So we have to turn to another set of tools to be able to sort of isolate the managed side. So the first one is one called HeapShot. This is an older Mono profiler that is useful for Xamarin iOS, and it gives you some very raw data about your application. And where it really is useful is that it's very fast. It tends to be low overhead, and it can collect a lot of data quickly right from within inside Zermatt Studio. You can get to it through the project menu and the Run Memory Analysis menu option. And it's free. You can use this without any sort of licensing. Then we have another tool that comes from Xamarin called the Xamarin Profiler. This is a newer tool, similar to HeapShot, but the difference is this provides a much better graphical experience of being able to really track things down through a full list of navigatable UI. And so we'll look at this tool in just a moment. Now be aware that this particular tool requires an enterprise MSDN license, but it's worth it just to get access to the profiler tools. However, Xamarin Profiler, while it works in both Xamarin Studio and Visual Studio, is only useful for Xamarin iOS and Xamarin Android apps. If you want to be able to profile Windows apps, then we have to turn to a different profiler, which is the Visual Studio profiler. Now, this is integrated into Visual Studio and again comes with an Enterprise MSDN license, and it lets you profile desktop, web, and Windows apps, including the mobile UWP applications. And you can see both CPU and memory statistics with these tools. Now, any of these tools can be useful in tracking down strange behavior in an application, and generally what you want to look for are odd patterns. In other words, allocated objects that you see in the heap that you don't expect to see. And so, as an example, if I have a couple of screens in my app and I go back and forth between those screens, I very likely wouldn't expect to see a whole bunch of the second navigation screen still in memory once a GC occurs. Right? Those would be transient objects that we expect to go away. If I continue to see them build up or load up in memory, that indicates an issue or a memory leak within my application. So we're going to look for objects that we're directly responsible for allocating that have an unusually high count to them. And those sorts of patterns are the sorts of things that we're going to look for. So since we're primarily talking about Xamarin iOS and Xamarin Android in this module, let's take a closer look at the Xamarin Profiler. So I mentioned Xamarin Profiler is a relatively new tool. It's still in preview status, at least as of right now, and it runs on both Windows and Mac OS. And we can use it to essentially do memory and CPU analysis on our Xamarin iOS and Android applications. It also supports Mac applications as well. Now, the UI itself, if it looks a little odd, it's probably because you've not used instruments before, because it's modeled off of the Apple Profiler tool. And it actually has two different profilers available today. We have an allocations profiler that allows us to track memory allocations, and a time profiler that allows us to track CPU and performance. And remember that this requires an MSDN Enterprise license. Now, the profiler is a separate application from the IDE, and it can be launched directly from the IDE, or it can be used as a standalone app. In Xamarin Studio, you'll use the Run menu and Start Profiling option. In Visual Studio, there's an Analyze menu, and the Xamarin Profiler option is there inside that menu in Visual Studio. You can also open up MLPD files, which have been produced by the Monolog Profiler, which is another tool that you can download. And again, that tool is free. It generates a log file, and then you can analyze those log files with this profiler. So to give you an idea of how to use the profiler, I'm going to use it here on the Mac and profile an existing iOS application, specifically one called XAMDraw that we use in our iOS Touch class. And I've got it loaded here in Xamarin Studio, and I can just go to the Run Start Profiling option here. That'll build the application if necessary, launch the Xamarin Profiler, and set up the app to be profiled. Now, the first thing it's going to ask me here is, what template would I like to use? And so notice that we've got several instruments here that we can actually utilize. The top one, All Profilers, just uses all the instruments. But then we have some subcategories. For example, I can watch allocations. I can see objects being allocated and track their allocations and the destruction of them. I can also look for reference cycles where I've got object A referencing B, referencing C that references A, and it'll detect some of those sorts of cycles there. We've also got a memory instrument, which basically is a combination of these two. And then we've got performance and a time profiler. And performance is both memory and the time profile, and then time profiler is just a CPU performance counter. So I'm going to just go ahead and select all profilers and hit choose. It'll use the same device and app that I had configured in Xamarin Studio, and you can see that it's launching the simulator to run the application here. So the app will come up and it starts reading data, and you can see that I'm getting some allocations here already. And what I like to do when the app launches is to go ahead and take a snapshot once the app is settled down. And I'm going to do that by clicking the little camera button here in the toolbar. And notice that I'll get a little camera in my timeline as well. And this just indicates that this is a snapshot that we've taken. Now let me just run you really quickly through the UI here. So these are my instruments that I have set up, and I can select each one of them by simply clicking between them. And so you can see here's the time profiler and how much time it's taken to actually execute these methods. We're going to stay on the allocations one here because we're interested in memory allocation. Then down here in the UI, you can see that I have some tabs that run across here that just give me access to various things. And so notice I can go to a call tree tab that simply shows the methods and the call stacks that have allocated the most memory. I've got an allocations list. This will get filled out once the app is ended. And then I have my snapshots that actually shows me what each of my snapshots are. I only have one right now because we've only taken a single snapshot. And then there's a console that's just simply the debug console coming from the app itself. Over here on the summary, you can see all of the allocations that have occurred, and then we've got a little sidebar here that you can turn on and off by clicking the little sidebar button. And notice that there's a single option here with a checkbox, only persistent objects. If I check that, it's only going to show me the objects that are currently still alive. And so by unchecking this, you can see the entire object graph that was created from the application from the very beginning all the way to the end, including all of the collected objects. Generally speaking, you're going to want to just look at persistent objects when you're identifying memory leaks. But if you're trying to see your overall picture of memory allocations, it can be useful to uncheck this to be able to see everything. And then down here at the bottom, there is a filter to be able to just identify things based upon their name. And so, for example, if I were just looking for view controllers, I could start typing view controller and notice that my list is now restricted to just the view controllers. And I can see there's a single view controller here, and it's 48 bytes in size. I can then click the X to get rid of that filter and go back to the full unfiltered list. And then finally over here on the right, notice that we have some statistics that just simply show us how much memory's been allocated, how many objects we've had allocated, how many are still alive, the private bytes, the working set, and then the virtual bytes in terms of the application itself. And notice that as I uncheck this, my allocations, my statistics themselves will change based upon whether or not we're only looking at persistent objects, things that are still alive. Okay, so let's start looking at this app in a little more detail. So I'm going to go back to the application here, and this is a touch application. And so as I click and touch or simulate a touch, it'll actually draw lines. And so notice that each unique touch gets a different color. And if I hold the Option key, I can simulate two simultaneous touches that are occurring. And then I could take a snapshot again in order to just see what changed between the first snapshot and the second one. In other words, what did we see get allocated over here? If I switch over to my snapshot views and I look at snapshot 1 here, I'm only interested in new objects. And so I'm going to make sure that my sidebar has the only new objects checked, which should be checked by default. And you can see over here all of the objects that were allocated as part of this second snapshot. And I can also see how many object moves have occurred. In other words, as the heap gets compacted, as it moves from the nursery to the major heap, how many of those things have actually happened here. And so I'm going to start scanning this, and in particular, I'm going to go ahead and sort it by name so that everything is kind of sorted by name here. And I'm interested in the objects that I create. In other words, things that I know my app is directly interacting with. And so as I look through this list here, you can see that we've got some event handlers, we've got some thread, we've got a single thread object, we've got 7 color objects, and we have 741 UI images. That seems excessive to me. We've also got 7 touches. That matches our 7 color objects, and that makes sense. For each touch, we created a color that we want to use. And so I'm actually a little bit suspicious of this. 741 UI images, and I really don't see any images here. If I expand this, you can see all of the instances that were created and the timestamp that they were created in. And notice the size here. It thinks that this image is actually only 24 bytes. Now, we all know that the image is very likely much, much larger than 24 bytes. The problem here is that the profiler can only see the managed representation of that image. In other words, it's unaware really of how big the native representation is, which is where all the memory really is going to be located. So all the storage for the actual bits and the depth and all of that sort of things, the bits per pixel, whatever that happens to be, all of that storage is actually allocated on the iOS side, the native side, and therefore my representation here that I see in the profiler really doesn't show that, and so it's a little difficult for me to see exactly how big this image really, truly is. But you could pick one of these instances, and then over here on our sidebar, we can actually select a couple other tabs. So the first little button here, the first button is information. The second one gives you a stack trace, and this is a stack trace for where the object was allocated. And so you can see here that this actually was allocated as a result of our touches moved event that came from the system. That went to a draw line method, which in turn created an image through UI graphics get image from current image context. And so presumably, if we were to go look at the source code, we could go look at draw line and see a call to this method and know that that's where the image is actually being allocated from. And then you can see that a little further up the stack, we see some NS object stuff and do invoke some things to actually interoperate with the native UI image sort of method API. But this is where we're going to actually want to look, is inside this draw line. Now you can see that every single one of these images came from this location. So this is where our 741 images is coming from. The last little button that's here shows me whether or not this image is still in use. And so this is a references graph. It essentially walks the objects and determines who is referencing this UI image. And if you look at these images here, you can see that we don't have any references. Now, this is a preview of the profiler, and so sometimes it can get this a little bit wrong. I've seen cases where references don't show up, where it sometimes has references and vice versa, but 99% of the time it's actually going to be good data that you can rely on here. And what this is telling me is that we have a bunch of images that were allocated and they were eventually not referenced anymore, but we haven't collected them yet. And I can sort of verify that assumption if I go back to my summary tab over here and I constrain this to UI image. Let's just see what we have. So notice we have 741 images here. I'm going to take another snapshot, and I want you to notice what just happened. All of my images just went away. Okay, that tells us two things. Number one, it tells us that when you take a snapshot, the first thing that the profiler does is it forces a GC to happen. That's important to understand. We only want to see live things in those snapshots, and so the profiler goes ahead and injects a GC collect into your application to ensure that the memory is kind of as cleaned up as it can be when it takes the snapshot. The second thing that we can observe about this is every single one of my UI images went away, all 741 of them. And we have no UI images outstanding at this point because we said only persistent objects. And if I uncheck that, you can see that there they are. But if I keep this persistent objects checked, notice that they're all gone. So all of them were collected. Now, that's an important thing to understand in terms of this application because it tells us that we have a potential performance optimization that we can do here. This isn't a leak. The objects were collected, and they eventually would have been collected once the app does a GC, but it's using more memory than it needs to. Okay? And we could reproduce this if we hit clear, and then just draw another one and hit another snapshot. Notice that now we have 49 images here. And that's interesting because I only drew one line here, and so clearly this draw line is happening on every touch point. We sort of saw that in the stack trace. This is happening on touches move. So as my touch moves, we're recreating a new image every time to represent what this view is going to look like. If I do my snapshot one more time, notice all those images again go away because they're collected. So let's go look at the code and see how we can improve this particular case. So I'm going to go ahead and go into the XAM draw view controller where we saw that in the call stack. We saw that it happens in this draw line, and I'm going to start looking at this code here. And so I can see that we're getting a current context, and we're correctly disposing that context when we're finished. Let me just move these over. And I can see as I kind of go through this, here's where we're assigning the image right here, and we're doing it from get image from current image context. So I can see exactly that that's the stack trace. Now the question is what should I do to fix this issue? Well, we know that this is being called over and over and over again. In fact, if we do a find references, we'll see that the reference that we have here is the method definition itself, and then a single reference inside touch is moved, where we're calling this every single time that the touch itself moves. And so I know that this is being called over and over and over again. And so what I likely want to do here is go ahead and get rid of the existing image if it's there. And so let's do this. Let's say image draw, image, dot dispose. So if there is an image already associated with this image draw, this is the UI image, or the UI image view rather, that's in my view. If there's an image associated with that, I'm going to go ahead and dispose it right here before I reassign it to a new image. Now, what that's going to let me do is make sure that this native image actually goes away. And remember that it doesn't actually completely go away until we remove it from the view. And so it's not removed from the view just yet. The image view is still essentially going to be, or at least have it rendered. And then once we assign this new image, we'll actually force a new render. And so once we exit this and we exit the end image context and we go back to the main run loop for the app, a new draw would get triggered and we'd see the actual view get re-rendered. But by disposing this image right here, it means that we can just get rid of that image before we assign the new one. Now, as I look at this method, this sort of draws me into a couple other things. I can see a couple other native things being used here. In particular, notice that we're using a path, and we're creating this path and we're adding a bunch of lines into the path. I'm guessing that if we go back and look at our profiler, and we close this and we actually look for CG path here, I don't see any in this, but if I go to my allocation list and see how many paths we had created, notice that there's a ton of paths. So we actually created a whole bunch of paths. If I say get rid of the only persistent objects, I can see that we actually created 797 paths over the life of this application. That again is a lot. And again, they did get cleaned up because when I check this, they're clearly not there anymore. But this is another native object that represents some amount of space on the native side, and because it's an NS object, we can get rid of it. And so I'm going to do the same thing that we did on our context up there. I'm just going to wrap this in a using, use the path right here and add all the lines into the path. Let's go ahead and make sure that we keep all that code in there as well. So we draw the path into the graphics context. And then once we're done with the path and we've drawn it into the graphics context, we can dispose it and then reassign our image. Okay? So let's go ahead and run this again. I don't want to run it, I actually want to profile it again. Let's go ahead and profile it again and see if that helped our image usage. I'm just going to again say all profilers. It'll update the app, relaunch it. The app comes up. Let's take our initial snapshot. Let's go ahead and draw a few things on the screen here. All right, so we can see we have a bunch of stuff. Let's go ahead and take a second snapshot, and let's go look at our snapshot. So now as I look at the snapshot, and again, I'm going to sort it by name just so that I can easily kind of see what's happening here. I notice that I still have an image, but notice now I just have one image. And that's important. It means that we got rid of all those images a lot earlier. It didn't require a GC collect necessarily to actually get rid of the images, the native images themselves, because we disposed them and that made them go away from a native perspective a little bit earlier. If I look at my summary side, let's just look and see how many CG paths we have here. So notice I have 367, but from a persistence perspective, they're all gone. All right, so they've been collected and they're now gone. Now, why did this happen? Why did it actually make a change in terms of the collection itself? Because we all know that calling dispose doesn't actually force a collection, right? So calling dispose simply disconnects the native side from the managed side. Well, what's happening here is because we disposed the image, we were able to tell iOS that this image is no longer valid, and it was able to deallocate that image, which means the next time our GC ran, it recognized that the image was already gone on the iOS side, and so it was able to collect the managed side when it did the GC as part of the snapshot, versus keeping that object around because the native object was still potentially in use. So it looks like we've correctly cleaned some of this up. Now we still have a single image here, and if we look in here, we can see that there's no references to it apparently, and we don't even have a stack trace, and so it really isn't giving us any information related to where it is. But presumably this is again coming from our draw line method. But having only one is perfectly adequate. We've successfully cleaned this up. And we could continue looking for other things in here just to see if there's other places where we potentially could optimize some of the code here. Now, if you don't have access to a profiler, another way to identify memory leaks in your apps is to watch for unbounded growth in the major or large object space heaps. And you can monitor this through the debug logs. Now, if you're unfamiliar with the debug logs, this is essentially output that's emitted in your output log that indicates when garbage collections are occurring. This happens in Android automatically, so debug logging is always turned on for debug builds in Android. But in iOS, you have to set a couple of environment variables. We talk about that in the XAM370 class, where we show you how to establish those environment variables. So if you're unfamiliar with that, you can either look that up in the documentation, or you can go look at the XAM370 materials to see exactly how to set those. But once you've done that, then you'll start to see output in your debug log that indicates when garbage collection occurs. And what you're looking for are the GC major lines. And so here you can see one on the screen, and it indicates how long the GC took, so you can see the total time, and it also indicates two numbers that you see on the screen here. And these two numbers are how much memory is currently in use by the major generation, so that's generation 1. In this case, you can see it's actually just a little bit over 1 megabyte. And you can see how much memory was in use prior to this collect. So it's showing you both after the collect has finished and then what it was before the collection. And then you can see a second set of numbers, which is prefaced with LOS. That's the large object space. And so those are large objects, things that are over 8K in size in mono. And in this case, you can see that we're using 64K of large object space. Now, what you're going to want to look for in these two values are where the first number is larger than the second number. All right, and so what that indicates is memory growth. And if you see that pattern continually through your app, in other words, it never seems to go down, then you have a perpetual memory leak. Now, be aware that most applications, at least statistically speaking, will run and they'll hit some point where they'll stabilize. In other words, it's expected to see memory growth for some period of time, particularly through an application launch sequence. And at some point, typically, the application will stabilize and it'll hit a threshold where it doesn't really grow much beyond that. And so it may go up and down slightly from that point, but generally speaking, there's some sort of line or threshold that the application hits that it tends to be its baseline. If you see your application continuing to go up in memory usage, it indicates a significant problem in your app, and it's something that you'll need to look for. And so you want to watch these debug log values to kind of indicate whether or not you have an issue. Now, if you see them going up, at this point, we need to start diagnosing where is the problem. Now, again, profilers are the most useful tool for that. And so you should definitely look at a profiler and see if you can get access to one in order to identify memory leaks. However, there are some coding techniques you can use as well. And the first one we can use is called a weak reference. Now, if you're not familiar with weak references, they essentially allow us to be able to identify when something has not been collected. And you can use them as a diagnostic tool by wrapping them around objects that you expect to be collected. And so here you can see we've got a data loader. And we're going to wrap our data loader in a weak reference object, and then we're going to use the data loader, that's the ... and then we're going to set the data loader to null. We're going to do a GC collect at some point, and we're going to say, okay, we expect that data loader will go away. We don't have a live reference to it anymore. It's now been nulled out. And then we can ask the weak reference, is the data loader still alive? And if it is, we can output something to our debug log indicating that we have a problem, that data loader itself is not being collected the way we expect it to be. Now, clearly we have to have some indication that data loader is our issue. And that's where sort of the memory growth and things like that will help. And this is one of those areas where profilers can be immensely helpful because they can point you in the direction of the objects that are still on the heap. Now, for those of you that aren't that familiar with weak references, you might be wondering how that actually works. Well, a weak reference is a special object in the Mono runtime and the .NET runtime. And the idea behind it is that it represents an object that the GC itself will ignore. And so it's a wrapper around an existing managed object, but it doesn't keep that object reference alive. However, it allows us to go back to the weak reference and ask, is this object still alive? And if it is, we can get a reference to it that then becomes a live reference, and we can then use that reference. We often use weak references for caching purposes, to where I have an object that I create and I'm going to use, and I'm going to hold in a weak reference so that if I get a second call or a subsequent call to use that object, and it hasn't been collected yet, I can continue to use the same instance. But if it has been collected, then I can simply recreate it. So it's objects that are easily recreatable that I don't want to hold in memory. But what we're referring to here, at least in terms of this particular usage, is we're using it as a diagnostic tool. In other words, we think that this object is not going to be collected properly, and therefore we'll use a weak reference to truly identify that that's the case. Now, if you're looking at that little bit of code there and you wonder, how can I make this a little more generic? Here's an alternative. Here we have a memory leak check class, and it allows us to essentially pass in an object. And notice that we can also pass in the caller file path and the caller line number, so that when we do the check against this object, we can actually output to say where this object was allocated. And so this allows us to indicate that this particular object is still alive when we didn't expect it to be. And so this is a little handy wrapper class that you can utilize in your code to be able to take weak references and use them as a diagnostic tool. Now, another thing that we can use that we can put in our toolbox is finalizers. Finalizers are a last chance mechanism for us to be able to do some kind of native handle cleanup on our objects. Now, we talk a lot about finalizers in the XAM370 class, and so you'll see exactly how they work and what really happens under the covers and how they interact with the GC process. But for the purposes of this discussion, we're using them again as a diagnostic aid. And the idea is that we can add a finalizer to our object that outputs when the object is about to be collected. So the idea behind a finalizer is there's a method call that occurs just before the GC actually collects your object. Now, be aware that that just before is not deterministic. In other words, it gets outputted to the debug console here, I think I'm about to be collected, at the point at which the finalizer actually decides that there are no more live references to this object. And so it's a dedicated thread that runs. Again, we have all the details about this in our XAM370 class. Notice that we're wrapping it with an if debug. We only want to execute this code if we're in debug builds. All right, so I want you to remember, as we talk about in XAM370, finalizers are very expensive, both in allocation terms as well as collection terms. So they have an impact on garbage collector and they have an impact on the allocation of the object. Both time and space are concerns when we use finalizers. And so we only want to use this as a diagnostic aid, and so therefore we'll always have an if debug around it. But the idea is I can use this to ensure that an object is being collected. And therefore I can use it to output to say, yes, I can see this is being collected and that is being collected. And then I watch for the output that doesn't happen. So where I notice that this object does not get collected, I go, aha, that's an issue. For some reason that particular object was not finalized and therefore the GC did not actually collect it. Now, where should we look for memory leaks? So the most common form of memory leak, at least in .NET applications, is in delegate references. So we can have other forms of leaks as well. As I mentioned, you could potentially be holding something in a list, or maybe you have it in a dictionary and you don't realize it, didn't get removed properly. But the most common form, at least the one most programmers run into, is with events and delegates. And so let me give you an example. Here we have an iOS view controller that's using the NS notification API. This is a service in iOS that allows us to handle notifications. And maybe this is a game application where I want to know when the device goes on battery power so I can throttle back my refresh rate and I'm not actually updating at 60 frames a second. Instead, I go drop down to 30 frames a second or something like that. And so I go to NS Notification Center and I say default center add observer for battery state did change notification. And I point it at a delegate. So notice I'm passing in a method on charging changed that is just a delegate that takes an NS notification object. So in this particular case, NS Notification Service is a built-in iOS service that provides a publishing, subscribing sort of messaging system. And we add observers using string-based keys. In this case, we have a constant off of UI device called battery state did change notification, and we pass in a delegate, in this case, on charging changed. Now, why is this an issue? Well, when you wire up a .NET delegate to an instance method like what you see there, then it has to hold a reference to the owning instance. And so the reality is our default center add observer onChargingChanged really is shorthand for this .onChargingChanged, which is really shorthand for new action NS notification this onChargingChanged. So it's really a delegate wrapper, but C# gives us the nice syntactic sugar to be able to just pass in a method name, and it turns it into that final representation there. So the compiler is doing that. But you need to recognize that this is really an object that's being allocated and it's being passed our method instance along with our this reference. Now, what that means is if we look at the action of T, it really derives from a class called delegate. Now, we're playing a little bit of a technical game here. It really derives from a class called multicast delegate, and that in itself derives from delegate, but for simplicity purposes, let's just call it delegate. And notice that delegate has two methods, or two properties rather, of interest here. And the first is the target. And notice it's just an object. That's our this reference. It actually takes a reference, a live pointer to the this reference of our onChargingChanged. And then we have a method info. That's some runtime information that tells it how to call the onChargingChanged method on the target. And so that way the system knows exactly how to invoke the delegate when it gets a call to say, I want to actually call the method that you're tied to. Now, why is this an issue? Well, the reason it's an issue is because our view controller is only supposed to live long enough to display the screen and then get dismissed. And so presumably this is a game screen and we have a start screen and we press the start button and we navigate to our game screen and the game screen wires into the battery change notification. We play our game, we die, we go back to the start screen or maybe a high score screen and the game screen itself is destroyed. The problem is we're wired up to NS Notification Center. And NS Notification Center happens to be a static thing, which means it lives forever. It's a live, static root that will never be collected. And because we have a notification wired up to our view controller, right, to our view controller instance for this battery state did change, we will now be holding a live reference from our static NS Notification Center to that view controller, which means the view controller cannot be collected. So it will live forever even though we're not using it anymore. Even though we actually within our application code can't get to that view controller anymore. But because the delegate reference is holding on to it from Notification Center, the garbage collector cannot collect it. So this is a problem. So how do we solve it? Well, ultimately, the advice that you should always follow in any managed application is if you wire up an event somewhere, you should always unwire from it. And so I'm going to move our NS notification wire up out of the view did load, and instead I'm going to use a pair of methods here, view did appear and view did disappear. And in our view did appear, we're going to go ahead and add in our code to add the observer. So notice here, we're going to say, okay, add observer, battery state change notification, onChargingChanged. And notice I'm caching off the return value from that. That comes back as an NS object, which is sort of like system object in iOS. And it just represents something that is a token of some kind. And in my view did disappear, I'm going to go back to that NS Notification Center and I'm going to say remove the observer from the token. So I'm going to pass in the token that represents this observer, and I'm going to ask the NS Notification Center to go ahead and throw that delegate away. This will unhook it from the chain, and we will no longer have a live reference to our view controller. This solves the problem. Now, the key thing and the key piece of advice here is if you wire up a delegate, you should always have some corresponding unwire from that delegate, which means you need a pair of methods here. And the reason we're not using view did load is because view did load sometimes will only happen once. I can hold a view did load, or I can create a view controller rather. I can push it on the navigation stack, pop it off, and then push it back on. I won't see another view did load because it was already loaded. But I will see another view did appear. The other reason is there isn't a corresponding unload. Now, I say that, and you'll go and you'll look at the method overrides that are on view controller, and you go, well, yes, there is. There is a view did unload, and you're right, there is actually a method override for it, but iOS doesn't call it anymore. So that method is actually, or that notification rather, has actually been deprecated. And so really the best place in iOS to do something like this is view did appear and view did disappear. And so you'll find similar patterns in the other platforms as well. And so Java, or rather Android, has a similar pair of methods you can use on your activity. In Xamarin Forms, we have an on appearing, on disappearing sort of notification that you can use. And so you'll find places to be able to do this. But the key thing is you want to make sure to unwire from events. Now, there's one case where you may not care. And that is if the object that you're using as a subscriber, in other words, our view controller in this particular example, if it never goes away, in other words, maybe it's the main screen to our app, and that main screen will always be alive. So the only time that the main screen goes away is when our app is actually terminated. Then I don't care as much about unwiring from a delegate. It's still not a good practice, but it won't actually cause a memory leak because we're going to hold a strong reference to it outside the delegate anyway. And so it's not like the garbage collector could have collected the object even if I unwired from it. So in that particular instance, you can play a little bit loose with the rules and not unwire from delegates, but I'm going to just tell you straight out that it's a good practice to get into to always look for this sort of pattern where I wire into a delegate chain and I don't unwire from it. So check your code for things like that. So here I am in Zermatt Studio on a Mac, and I've got a little project here, network state, that I'm just going to go ahead and run in the simulator just to show you what it does. And this application has a bit of a problem, and I want to show you exactly what's happening. So notice the main page just comes in, and it has a button here, Show Network State. And when I click it, I just get a green box. This box will be red if I don't have a Wi-Fi connection or a network connection of some kind. And so if I turn off my network connection, we would see that this would actually change. And so notice I turned off my Wi-Fi, and then I get a problem page red. If I turn my Wi-Fi back on, you can see it goes back to green. The key thing with this is each time I go back, we're back on the main page, and then I can come back to my problem page and back, show network status, back, show network status, back. And the goal is to actually clean up that second page every single time. And so I've got a little button here, GC, because again, GCs don't happen all the time in iOS, but I can click this and I can force a GC, and you can see that I've got my debug log turned on. Remember that to do that, you have to go to your iOS project. You go to the Run option here under General, and you set these two environment variables, mono log level to debug and mono log mask to GC. And then we'll start seeing GC messages. And the key thing I want to watch here is this major size. And so notice it was 2304, it's now 2976. If I do this a few more times, and I hit GC again, I look over here, it was 2976, and now it's 3104. And I could keep doing this, and I'll continue to see my memory going up. If you have access to the profiler, then this actually gets to be a little bit easier. We can run the profiler, and we'll see exactly the same problem, but it'll even point out exactly where the leak is, which that's really useful. And so if we try that, and we say all profilers, let the app launch, we take our initial snapshot once the app settles, and so I'm going to take a snapshot, I'm going to show my network state, go back, show my network state, go back, show my network state, go back. I go ahead and take another snapshot. If I go back and look at these snapshots, and again, I'm going to look for things that are mine. And so in this particular case, this app has a namespace of network state. So once I sort by name, I can see network state problem page, and I can see that there's 3 of them. Well, we shouldn't have any of them. Once a GC runs, all of these pages should be collected. And if I do this a couple more times, I did it 3 more times, I do another snapshot, look at this snapshot, and I can see that, gosh, there's 3 more. And if I go over and look at my summary with only persistent objects and say network state, I can see that I have 6 of the problem pages, only 1 of the main pages, 1 app, and then 1 app delegate. So these 3 are fine, but this problem page is an issue. Now back on snapshots, if I pick one of these instances, and I go and look at the allocation chain, you can see that it was allocated as part of the touch up inside on our main page. We went to the next page, and then that actually is what created the page. If I go to the last page here, you can see that we do have references here. Now, I'm not going to blow the surprise. You can probably see it right there, but let's go and see how we could possibly diagnose this, knowing that it's problem page inside the app itself. And so I'm going to go into problem page and just look at the code. Now you probably noticed in that stack trace that we had an interesting thing in there, which was this cross-connectivity event. And we know from the slides that we just saw, events and delegates are always trouble. We always need to watch our events and delegates. And let's just verify, if we didn't have a profiler, how we would know that this page is our problem. Because it seems like I go there, I come back, I go there, I come back, I go there, I come back. My memory goes up and doesn't seem to go down. So we're going to use a finalizer for this. I'm going to create a finalizer for my problem page. I'm going to put an if debug around this. And we're just going to go ahead and write out to the console. Actually, let's use debug write line. We could use console as well. I just don't want to pull in everything that goes with that. So let's do a debug write line, and let's say cleaning up problem page. And we can even put out like the hash code for it or something like that. We'll do it as a hexadecimal. Let's go ahead and put into the constructor the same sort of output. So allocating problem page, and we'll output the hash code. And you could even get a little bit tricky if you wanted to. So one thing I've seen some people do is something like this. let's stick in here a static int counter. And then here, let's go ahead and increment it. So we'll say interlocked increment ref counter. This will return me the new value once it's incremented. And let's do the same thing here. Instances, and we'll say interlocked decrement ref counter. And that'll just tell me how many we have left once this comes through. Okay, so let's try this. Now, what we're going to get out of this when we run it is a count. Every time that page is allocated, we'll see the counter go up, and every time the page that we think the page is being destroyed, we'll see it go down. Keep in mind, remember that finalizers are not destructors. They don't actually indicate that the page has been garbage collected, but it's the last step before the object is garbage collected. So we go ahead and go to the page. I see I have one instance. I go back. I don't see it being cleaned up. I now have 2 instances, 3 instances. I do a GC to force it to be cleaned up, and I can see that none of those are going away. We've successfully identified and said, yes, this is our problem. It is problem page. Now, why is it not going away? Well, remember our events discussion. Events keep things alive, potentially, and this is particularly an issue if the publisher, in other words, cross-connectivity current, outlives the subscriber problem page, which is exactly the case here. And when that happens, we have to make sure that we unsubscribe. And generally speaking, you should always make sure to unsubscribe. But in particular, in this case where we have disparate lifetimes between the two objects, we want to make sure to do that. And so we're going to go ahead and override the onAppearing method. And we're going to go ahead and wire up to that event in onAppearing. And then I'm going to override the onDisappearing. And I'm going to unwire from that event in onDisappearing. So we use minus equal here. And let's run it again and let's see what happens. So now we're correctly getting rid of our event notification when this screen goes away. So we wire it up when the screen first shows up on the screen, and we get rid of it when it goes away. So I say show network status. I see 1 instance. I go back. I see 2 instances. I go back. I see 3 instances. I go back. I hit GC, and I see 2 instances, 1 instance, 0 instance. All 3 of those have now been cleaned up. And if I ran this in the profiler, I would see that my problem went away there as well. So profilers are incredibly handy, but even if you don't have one, you can start narrowing down the issue by looking for the pattern of where your memory seems to increase. In our case, it was when we went to this second screen, we saw that memory continued to go up. But you have to kind of narrow it down. And once you do that, then you can use other techniques like debug finalizers like you see here with counters to be able to track those objects. And we could use weak references here as well. This is just an alternative way to do this. So the second place that we'll sometimes run into memory leaks is in thread locals. Now this particular issue is far less common than with the delegate chain that we just looked at. So let me explain exactly what happens here. A thread local is a reference which is unique on a per thread basis. In other words, each thread that accesses the reference gets a unique storage value for it. And in this particular case, this bit of magic is actually performed by tracking the thread that accesses the value and then returning a unique object based upon the calling thread. And so here you can see some code where we're allocating a thread local random. And by the way, the same problem occurs if you use the thread static attribute. But this is a more modern form of thread static of using thread local. And so in this case, I'm creating a thread local random. What that means is that every thread that touches this particular type or this value of RNG will get a unique random object. Notice that it has a constructor that is essentially a delegate function, and that delegate function is responsible for returning the object that the thread will access. And so in this case, every thread that accesses it, it'll call this delegate function and we'll create a new random object with a unique hash code passed in so that we start at a unique place. This will make sure that if 2 threads touch the object at the same time, they don't start at the same sequence location for our random number generator. Now, why would we want to do this? Well, random, it turns out, is not thread safe. And so if you call next on multiple threads, you will get back the same values every time. And they'll just be in lockstep. You'll get the same value every time you call it from all the threads that are calling it concurrently. And so in order to ensure that each thread gets its own unique set of random number generated values, we will allocate a new random object per thread. And then we're going to use that inside of a parallel for. So remember, parallel for is a TPL construct that allows us to essentially do a for loop across multiple threads, passing in the start and end values, and then a delegate to execute on each index, where the delegate itself is going to be called by multiple threads concurrently. And so in this case, inside the thread body, so notice we're going to take that RNG, and we're going to say, give me the value, that will give me my random object. The very first time a thread touches the thread local, it will allocate the random object for us. Subsequent references to that particular value will return the random that was allocated for the thread. And so the value gets cached off. We'll go ahead and get a value. We'll do a next for 100. That gives us a random number. We'll use it in the context of this body. Now, What's the problem with this? Well, the problem is that each thread that touches this gets a unique object, and we can't get rid of this object until the thread itself goes away. So as an example, here we have 4 threads that all touch RNG value. And so notice as soon as they touch it, they get a new random object. And we can see thread 1, thread 2, and thread 3 all end. And if we had a garbage collect that occurs right here, then thread 1 and 2 would collect their random objects. But thread 3 would not, because it didn't actually terminate until after the garbage collect occurred. And so if we have a second garbage collect, then notice thread 3's object goes away. But notice thread 4 is still there, because thread 4 is continuing to run. And this is particularly a problem when we use things like thread pools, which is exactly what Parallel 4 is going to take advantage of, because thread pool threads get reused. In other words, we pull a thread out of that pool, it does some unit of work for us, and then the thread moves back into the thread pool to service the next request that might come along. Now, sometimes those threads can be deallocated and go away, and sometimes they don't. It just depends upon the workload that's occurring within the app. And there are other threads, such as our main thread. If our main thread touched this RNG value, then that random value that's part of that thread local would never go away because the main thread is never going to terminate. And so we have to be a little bit careful about using thread locals because they can inadvertently cause a memory leak in the sense that we're not deallocating the values. So again, how do we fix this particular problem? Well, the way that we're going to actually do this is by making sure that when we're finished with the thread local, that we call dispose on it. So it turns out thread local of t is disposable, and when we call dispose on thread local of t, it'll get rid of all of the thread local values. Now, it presumes, of course, that those threads aren't going to touch that thread local again. If they do, they'll get an object disposed exception, and so you have to make sure that you're truly done with the object. But this is the correct pattern in terms of utilizing a thread local value. So make sure that once you're finished with the thread local of t, that you go ahead and call dispose on it. Now, that sort of wraps up kind of the common sort of memory leaks that we'll see inside of our managed applications, regardless of what sort of platform we're sitting on. And by the way, a lot of these same issues occur in the Java platform as well. And so even though they're slightly different names and maybe different classes that we'll utilize, we have exactly the same problem in the Java world because it's a garbage collected environment. And so when we hold on to a live reference to something, a strong reference, that means that the garbage collector can't kick in and release that reference. And so even if we're unaware that we're holding a reference, it's going to be a problem in our application. So now that we've seen those, let's switch gears a little bit and let's talk more about iOS-specific issues that are going to happen inside your Xamarin iOS applications. So to start with, let's talk a little bit about how iOS manages memory. So we know that in .NET and Mono we use a garbage collector, but it turns out that iOS does not. iOS uses a different management technique called reference counting, and this is where we maintain some sort of integer count for every object that we allocate. Now, if you've worked with Microsoft technologies for a long time, then you're going to be familiar with this paradigm because it's exactly the way COM works, or WinRT for that matter, which is based upon COM. As you can see here, we're going to allocate an NS object that's just a base object in iOS, and the equivalent Objective-C statement would be alloc init, and so that's the pattern that we use. We allocate and initialize the object. We use the little brackets to indicate message calls that are being made to that object, and we have what's called a retain count. That's the same as the reference count in COM, and it starts out at 1. And so when we allocate and init our object, the retain count is 1. When we do a retain against that object, that's a copy of the reference, and that increments the retain count, and therefore now our retain count is 2, and we have 2 values pointing at the same object, A and B. We then call release on one of those objects. Our retain count is then decremented and becomes 1. And now we only have one valid pointer to that object, which would be B in this case. And then finally, we're going to call release on the B instance. That will then decrement the retain count to 0, at which point the memory is deallocated by the iOS runtime and the object goes away. This same exact pattern is used in the COM world. We just use different method names to be able to invoke it. There it's going to be called query interface, add ref, and release. In this world, it's called alloc, retain, and release, but the principles are identical. As long as that retain count is 1 or higher, the object is alive and well and sits in memory. As soon as it hits 0, at that point the system automatically deallocates it. But the point is this is a manual system. In other words, we have to execute these calls within our code in order to manage the lifetime of the object. Now, for those of you that have worked a little bit with Apple's technologies, you might be familiar with ARC, or what's called automatic reference counting. This is a language construct that's part of the compiler that allows the system to sort of manage some of this reference counting for you. In other words, it will automatically do retains and releases based upon what you do with the objects in your code. And in fact, Microsoft's C++ compiler for WinRT has a similar construct built into it as well, where they're going to manage a lot of the add-ref release calls that are being made to the WinRT objects. However, even with some of the automatic reference counting that's built into the compiler, this can still cause dangling pointers and memory leaks within our applications. And so it's not a fix-all for our application. It's still an issue for Objective-C developers today when they're trying to manage their objects and manage their memory. Now, when native iOS objects are accessed in your C# code, the runtime in Xamarin iOS creates a special wrapper to represent that native object. So you remember when we started this talk, we talked about the two different types of memory. We've got the native memory that we're allocating our native objects out of, and then we have our managed memory that's going to be sort of collected automatically by the managed runtime. So when we allocate a native object and we're going to use it from C#, we create a peer object to represent it in the managed world. This peer object has a pointer to a handle, so it's an int pointer, that's being held onto that represents the native object in the iOS world. And so when we make calls to the UI button and go and set its title or set its background color or add in a border or something like that, adjust its layer, all of those things are actually messages that are being sent to the native UI button on the iOS side through that handle. And so we use that handle to actually hold on to the UI button and keep it alive. And there's a one-to-one relationship between the peer object that is allocated and maintained by the Xamarin iOS runtime and the UI button that is allocated and maintained by the reference count or the retain count in the iOS runtime. The way that this works is the system actually automatically deals with the retain count for you. And so when you do a new UI button in Xamarin iOS, under the covers, it's going to do an alloc init. And it's going to have a retain count on that native int pointer, which will be 1. When we set it to null, our button, and assuming that there are no other references to it, a GC collect occurs. At that point, the system will take that int pointer and it will do a release. And it does it through a finalizer. So it uses the finalizer system in order to automatically release handles, which is exactly what finalizers were built for. And so this allocation and deallocation happens automatically under the covers as part of the creation and destruction of the managed object itself. Now notice that this depends upon the GC running. So it means that this is not a deterministic operation. The GC runs when it needs to run. And so it could be an unknown amount of time between the point at which we actually null out the reference to the button and the point at which the GC collect occurs, a finalize occurs, and we actually release the int pointer that represents the true UI button under the covers. And so for big objects like images or huge object graphs, this could be a problem from a memory perspective. And so there is a way to release the native iOS handle in a more deterministic fashion, and that is by calling dispose. And so all of our native peers, anything that wraps a native object and holds that int pointer, always implements iDisposable. And actually this comes from even the base class of NSObject. So everything from NSObject forward implements iDisposable, which indicates that the object has some native resource that can be released prior to the garbage collect occurring. In this case, it's going to be whatever the native resource is, the UI button here. And so this interface, iDisposable, exposes a single method, dispose. If you want to get more details on that, we talk about this extensively in CSC 271, where we look at why the pattern exists and how you implement it and how you use it. But the idea is that if you've got a native iOS object and you want to make sure to release the native resources that are behind it, you call dispose on your managed peer object, and then it will automatically clean up that retain count and the object will go away, assuming again that iOS itself doesn't have a reference to it. So for instance, if I take my UI button and I put it into the visual tree, and so it's held onto by a view that's held onto by a view controller, even if I call dispose on the UI button, it won't necessarily go away. The native handle would stick around because the button itself is still in my UI. So both sides, again, have to agree that it's time to get rid of the object. You have to make sure to take it out of the visual tree and then call dispose, and that would then ultimately clean it up. Now there's two different kinds of peer objects that we're going to deal with in Xamarin iOS. The first is called framework peers. The second is called user peers. And these two different objects have two different memory sort of semantics. And so the way that they're handled or managed is going to be slightly different in terms of how they're tracked and released. And so let's go ahead and look at both of these, starting with framework peers. So framework peers are built-in types that have been created and shipped with Xamarin iOS. And so the managed wrappers themselves are all part of the Xamarin iOS Runtime DLL. So this is going to be pretty much the majority of the base classes that you're going to work with. And so these are types that are things like UI view controller, UI view, UI button, MK map view, all the sort of types that you'll directly work with that represent the actual native things that are part of iOS itself. So the important thing to understand about framework peers is that they're completely stateless. And so when we execute code like what you see here in C#, where we do a new UI button, that will do a new alloc init, and then we do a set title to set the text for the button, and then we do a button current title to go retrieve that text and then compare it to a value. Really, under the covers, it's doing something like this, where we do a button set title and we pass in some text and we tell it what state we want that text assigned to, and then we go and we retrieve the current title from the button. So the only state that the managed peer has for a framework peer is the int pointer handle itself. Everything else is pushed over to the native iOS runtime. The framework peer just holds that handle so that it can retrieve and access the state and the methods that are available on the actual native object itself. Everything else is always contained inside the native object. So this provides for some interesting optimizations in the framework. First, Xamarin iOS only creates a framework peer when it needs to. The very first time that our managed code needs to interact with a runtime object, the system will automatically generate the framework peer for it. Let's say, for example, that I used a storyboard to create my UI, and that storyboard created a button. And in my C# code, I then go to the main view of my view controller and I say, give me the first subview of my view. And I know that it's a button, so I cast it to a UI button. What's going to happen under the covers is the system will go retrieve the int pointer from the native subviews collection. So again, remember, all the state is stored on the native side of the fence, on the actual UI view itself. And so we're going to access the subviews collection that's on the native iOS side. We'll retrieve an int pointer from that, which represents the UI view pointer. And then the Xamarin iOS runtime will automatically generate a UI button object, assign the int pointer to it, and hand it back to us as a UI button. This automatically happens anytime that we do a reference to something. And so up to this point, before we called subviews, no peer had been created. We didn't even know about the presence of that button on the managed side, on the mono side. But once we request an object from that subviews collection, Xamarin iOS automatically creates it for us. We get a new peer object to represent the button. It looks at the actual type by querying iOS, and it generates a correct framework peer for it and hands it back to us, and then we can interact with it through the normal properties and methods that are present on the framework peer. That also means that when we no longer have a reference to that framework peer, Xamarin iOS can collect it. And this has absolutely zero effect on the presence of the object on the runtime side. So remember I told you that if I were to do a dispose on that UI button, that it wouldn't necessarily get rid of it out of the visual tree. And that's why we can collect it here as well. And so in this case here, I have an action, and I'm being passed my UI button on my onShowDetails, and I'm going to use the button inside this method. But when I leave the scope of this method, I'm going to assume that we didn't actually cache it off anywhere, and therefore that UI button sender falls out of scope, and on the next garbage collection, the system will collect that UI button. And so that means that this past instance, when we get a second notification, so if I click the button a second time, it could actually be a different reference object. In other words, a different managed instance that represents exactly the same button could be passed to me. It will have the same int pointer value, so the handle will be identical because it's the same native object, but it's a different managed framework peer representing that button. This collection of peer objects only happens if I don't keep a managed reference to it. So if for example, I took that sender and I put it in a field that was in my class, well, then it has a live reference. The UI button reference itself will not be collected. And so what happens in that case is the second time I click that button, the system will actually look in a dictionary of weak references. So we saw weak references a little bit earlier. It looks in a dictionary of weak references that says, hey, do I have a managed framework peer for this int pointer handle? So when it gets an action, it gets the handle to the object. And it looks inside that dictionary of weak references, and if it finds a weak reference and the managed peer is still alive, which if I held it in a field it would be, then it will hand me back the exact same object. And that way I can do reference equality checks. And so as long as the peer has not been collected, I'll get back the same object every time I click this button. But if I don't hold a live reference to it, then the weak reference would get collected. And so when we look in the dictionary, it'll look at that object and say, nope, this object no longer exists. It will recreate a new managed peer, assign the handle, and pass it into my onShowDetails method. And so depending on how you structure your code, you may or may not get the same reference back again. And this is actually an optimization because it means that we don't have to hold all the memory on the managed side. Because again, all the state is on the native side. That's the advantage of this particular architecture. Let me give you a quick example I'm going to create a brand new iOS application, just a single view app. Let's just call it Test App. Say Create. And all I'm going to do is add into the view controller just a little bit of code. Let's add a new view in here. So let's say new UI view. Let's add in a frame. Let's put it at 50, 50, 100, 100. And let's set a background color. Now let's go ahead and throw this into a weak reference so that we can track it. And I'm going to go ahead and let this view just fall out of scope after I add it in. So let's go ahead and add this into our view hierarchy. And then in the view did appear, let's just check and see, is this weak reference alive? And then let's go ahead and pull the view back. It'll be the last thing in the subviews. And let's go ahead and output, just to make sure it's the same one, the frame. And so you can see that my rectangle came up here, and I can see that it's still alive. So let's fix that. It could just be that we didn't run a GC. So right here, let's just force one, and then see if that changes our output. And now notice that my output says false, but it definitely is that same rectangle, 50, 50, 100, 100. So let's see if we can actually identify it. Let's put in a console write line, created view, and let's dump out the hash code for the view. And let's also dump out the value of the handle. And I'm going to do the same thing down here, and you'll see something interesting, or at least I think it's interesting. So notice it runs. If I scroll up a little bit here, you can see that I got my created view, and I have 2048479.456 with a handle of 7A1950E0. If I scroll down and I look down here, I can see that it is false. In other words, my weak reference is saying that original object was collected, but if we look at the hash code, it's exactly the same. And of course the handle's the same. I expect this to be identical right here because this is the representation on the native side. In other words, that didn't go away, but this object did. And so if you use get hash code for reference identity, you might be a little bit surprised that it's the same hash code. But if you actually go and look at the implementation of get hash code, and so if we disassemble it here using the object view or assembly browser, you'll see that the implementation for get hash code on NS objects, this is our base object here, is actually this get native hash, get hash code. This is actually going against that int pointer, and so it's retrieving a hash code from the underlying iOS object and then using that as the hash code for our wrapper for our peer object. Which means that when you get a second peer object created for the handle, because the original one has been collected, the hash code will be identical. And ultimately what this means to you is that Xamarin iOS, the runtime, is trying to make it appear as if it's exactly the same object, because for all semantic purposes, it is the same object. It represents the same native handle, and therefore all of the properties and things that you'll access with it are going to be identical. Now, the second form of peer is called a user peer, and this one's a little bit different. This is where I have a custom managed object that's defined in my code base, which derives from a framework peer. And so here, notice that we're creating an object called footnote view that derives from UI view. And this UI view is obviously a framework peer. It's a class that exists in the Xamarin iOS runtime, but footnote view is not. It's a custom object that I've declared that's deriving from UI view that adds in some sort of state on top of the UI view itself. And so anytime that we create a custom type that derives from a framework peer, we are creating something called a user peer. And so here's an example. So user peers, here's our footnote view. Notice it derives from UI view, and it's got some managed state associated with it. Here we've got a footnote ID, and we have some footnote text, an integer and a string value. These fields that we've declared are part of the managed state of this object only. In other words, the native iOS side doesn't know anything about this state. It's strictly held on the mono side. What that means is that we have to hold on to this object in order to maintain this state because it's only on the managed side. And this becomes the key difference between a user peer and a framework peer. Framework peers can come and go because all the state is on the native side. So all we care about is that int pointer. And as long as we have access to that int pointer, we can recreate everything else about a framework peer. User peers, on the other hand, are sort of split. Some of the state is on the native side, some of the state is on the managed side. And so it means we have to treat it differently with regards to memory collection. And so having managed state changes how the runtime looks at this object. So notice here we have a viewDidLoad method. That's an override on our view controller. And we're adding into the view hierarchy a new footnote view. And I'm setting the ID and I'm setting the text. Now notice in our viewDidLoad, we are not holding on to the managed object. In other words, we didn't cache off a reference to footnote view. Instead, the only reference is in the native view hierarchy. So we've added it into the subviews collection of the main view of this view controller. Now remember I told you earlier that subviews is not on the managed side at all. Right? Subviews is actually just a collection on the native side, and so we'll get the int pointer from this new footnote view that we just created. It'll do an alloc init on the UI view base class. We'll end up with an int pointer. It'll insert that int pointer into the view, but it also has to track this footnote view object. We cannot get rid of it because it has its own set of state. A framework peer, on the other hand, could potentially be collected after we executed the add call. In other words, once we've created the object and we insert it into the visual graph, there's no reason to keep the framework peer around because there's no state to it. But the footnote view has state, and so we have to keep it around. So this highlights the difference between framework and user peers. Because these user peers have some additional state associated with them, the specific instance that we create has to be kept alive until we're done with it, and we can't collect it. So it means that when we retrieve our state, so for example here in our view did disappear override for our view controller, we're going to go into the subviews collection, and we're going to assume that it's the very first one, and we're going to go ahead and pull out that footnote view. If we collected the footnote view like we would a framework peer, then all of our managed state would be gone. But it won't be gone, because in this case, the system understands this is a custom type. It's not a type that's contained in the Xamarin iOS runtime. And by the way, that's exactly how it determines it. It says, what's the assembly that this type is contained in? And if it's not a known assembly to the Xamarin iOS runtime, then it's considered a user peer and it's treated differently. So in this case, the garbage collector would keep the object around, it'll keep a reference to it, and therefore when we retrieve it from the subviews collection, all of our state will be there because it's exactly the same wrapper. So the same exact instance is kept around. Now here's the idea in a more graphical picture. So notice that both of our managed objects, which are shown in blue here, the footnote view and the myView controller, both have state associated with them. And they hold on to a base class, which is a UI view, that also has state associated with them. Now, we don't keep a user reference to either the footnote view or the myView controller. So normally this would cause the GC to collect them. So in a normal .NET desktop-based app, if you don't have a live reference to footnote view or myView controller, they would get collected in the traditional .NET rules, right? That's the whole idea behind a garbage collector. No strong reference means that the object goes away. But in this case, the system's going to act a little bit differently. And it's going to create what's called a GC handle to that footnote view in the myView controller in order to force it to stay around. And what that means is that our retain count on the UI view itself is going to be bumped. So notice that our UI view retain count is now going to be 2 and our UI view controller is now going to be 2. That's because not only is the UI view in the view hierarchy, so that's the first retain count, but footnote view has a reference to it, and that's the second retain count, and because we have a GC handle to the footnote view, we're not going to release that retain count. Same thing for the myView controller, right? So we have a retains off of the myView controller class that's going to hold on to the UI view controller. That's going to increase the retain count to 1. And then, of course, the UI view controller is actually present and visible on the stack, so it's held on by the navigation controller root, and therefore the retain count will be 2 because it's on the native side as well. And then we're keeping the myView controller alive with a GC handle that roots it from the GC's perspective. So when the GC runs, as long as the user peer has a retain count greater than 1, then it will consider the object alive and uncollectible. Now, once the retain count hits 1, and there are no managed references, then it means that the managed object will be collected and the iOS object can get destroyed, because it essentially means that there is no visual graph for that object. And so that's really what it's looking at. It's looking at that retain count, and every time the GC system runs, that's what it's going to evaluate, is the retain count 1 or less? All right, and if it is, then the object gets destroyed. Now this brings up an interesting quandary. Because of the way the architecture is sort of set up, the fact that we're creating strong references outside of our code, it means that we can actually create a new possibility for a memory leak that's a little more insidious than just a delegate handle. Because the user peers get rooted, if they hold on to any other managed objects, then those objects are also effectively rooted, and it allows us to create cycles that the garbage collector itself cannot break. And so notice here, we've got 2 classes, myView controller and a footnote view that derives from UI view. And footnote view holds a reference to myView controller. In other words, it has a parent reference pointing back to the view controller. This is actually a pretty common scenario that people set up inside their managed code. And then at some point, I'm going to take my view controller and I'm going to add a new footnote view to the view controller itself, setting the parent to be the view controller reference. Now, here's what it's going to look like visually. This is going to create a strong reference cycle that the GC can't break. And so here is the same basic graph. So notice that we have a footnote view that has a GC handle that roots the footnote view. Because we didn't have a managed reference to it, you can see that we're only adding it to the myVC view tree. We've got the view controller. It does not need a GC root. We're assuming that we're holding on to that view controller because it's on the navigation stack, for example. We have a parent property from the footnote view that holds onto the view controller. And then, of course, the myView controller retains the UI view controller, and so it has a retain count of 2. And then our UI view controller on the native iOS side retains the UI view that represents the footnote view, and so it has a retain count of 2 because we have 2 retains against it. And so now what we have is a cycle here where the system cannot break this. Notice it's a nice little square where everything is sort of pointing at each other. This is something that garbage cutters normally are really good at breaking, and if this were strictly managed references, the GC system would have no trouble with identifying the fact that there aren't any references outside this, and it would be able to collect it. But in this particular case, because we're holding a GC handle root to that footnote view, it keeps the entire view graph alive. Now, when we go back to the previous view controller and I hit the back button, iOS will take the view controller off of the navigation stack, which will drop my retain count. So my retain count will go back to 1, but when the GC runs, the UI view is still going to have a retain count of 2 because it's being retained by the view controller and the GC handle root. And so we cannot collect the view controller because there's a live managed reference, which is rooted by the GC handle. And so this whole graph is considered live, even though our user code isn't holding on to it. So we've popped it off the navigation stack. We didn't keep a reference to any of these objects. But because of that GC handle and the fact that the UI view has a retain count of 2, and it's not 1 or less, the entire graph is kept in memory. And the GC can't break this. And ultimately, what that means is that we're going to end up leaking this entire object graph. We can't collect any of these objects, and if we show this view controller enough times, our application will ultimately get terminated because of an out-of-memory exception. So this is a significant problem that you have to watch out for, and this is exactly the sort of thing that the profiler would highlight for you. We'd see a bunch of footnote view objects in memory, and we'd go, why in the world do we have 50 footnote views? Right? We should only have at most 1 or 2. So the question becomes, how do we fix this? Well, it turns out that there are a couple of strategies that we can take. And all of them are going to accomplish the same goal. The goal is to break the strong reference cycle that's occurring between all these objects. So the first thing that we can do that will break the cycle is we can clear the parent property. And when we clear the parent property and the GC runs, then it will see that the retain count is only 1 on the view controller, and therefore it will release the native handle on the view controller. This will end up dropping the retain count on the view controller to 0, which will cause it to get cleaned up. Next, that will in turn drop the retain count on our view since the VC releases the view when it gets destroyed. Now our retain count on the UI view is only 1. And this is the signal for a user peer that says that the only reference that we have is our managed peer object, right? So if our retain count is 1, the only reason it's 1 is because the footnote view, which is our user peer, is holding on to it. And so therefore, when the GC runs, it'll get rid of the GC handle, which will then clear up that whole graph, and both of those objects will go away. So that's the first thing we can do. We can break the cycle by clearing the parent node. So here's another approach. We can also take our parent view controller and we can dispose it. This will have the same basic effect. When the GC runs, it'll see that the retain count is 1 on the view controller. It'll release the native handle and clean up the user peer. Again, we won't get a GC handle because the retain count is not greater than 1, and so it knows that iOS is not using the object. So our retain count drops to 0, which causes it to get cleaned up. It drops the retain count on our UI view because it's been removed from the visual graph. And therefore, when GC runs, it'll see, footnote view has a retain count of 1 on the native handle. Therefore, we're the only one using it. It'll clean that graph up. And then both of those objects can then go away because at that point, they're just managed objects. And so the GC will just run as it normally does. So here I am in Zermatt Studio on a Mac, and I've got a sample app here, User Peers, and it has a single view controller. And this view controller creates a custom parent view. And so I've got 2 views in here, a custom parent view and a custom child view. Both of these simply derive from UI view, and they've got some output when they get created and some output when they get disposed. And then you can see I've got a layout subviews that just creates the child view. Now notice that the child view has a reference to the parent. So this is a managed reference that's being used here. And in my view controller, I can add and remove these 2 views. And so you can see we're going to create 3 buttons. One will add the parent view, one removes the parent view, and then one does a GC. And so let's go ahead and run it just to watch the disposals, because in both the parent and the child, we're going to output to the debug log when it gets created and when it gets disposed, and we're going to go ahead and track a counter here, kind of like what we did in the other demo. So my app comes up, and I can add the custom views in, and notice I get my two views. This is the parent view, this is the child view. And notice that it shows me that I have two live instances, and when I tap on the child view, it changes the parent view's color. Notice if I tap on the parent view, nothing happens. So it's only on the child view that I get that, and that's the purpose of that reference, so that the child view can notify the parent that it's been tapped, and therefore we can change the background color. I can remove the parent view, which also removes the child, so now it's removed from my subview hierarchy. And notice that I don't see any disposals here, and in fact, if I do a collection, I still don't see anything happening here. I still see that I have two instances, one of the parent view, one of the child. If I add it again, now you can see I've got two. I remove it, I add it, now I have three. I remove it, I add it, now I have four. If I collect, again, nothing happens. Now, let's just look really quickly at the code that's removing that subview. So it's in this onRemove subviews. This is the method called from the button. And notice I'm just asking, do I have a parent view? If I do, let's remove it from the super view. That's what takes it out of the visual hierarchy. And then I'm setting it to null, which in most .NET applications would be a way of kind of getting rid of this reference. So it means that I no longer have a managed reference to that object, and therefore this parent view child view is now a self-contained cycle. So I have no references to it from my code, but yet we can see it's not being cleaned up. And the reason it's not being cleaned up is, again, because the parent view has the child view in its hierarchy. So we added the child view here, right? You can see it just got added as part of the constructor. And the child view has a managed reference back to that parent. And it's because of this that these two are kind of in this deathly embrace where they're not going to let go of each other. And remember, because these are both custom peers, these are user peer objects, Xamarin iOS will hold on to these references, and it will automatically create GC roots to ensure that they don't get collected prematurely. And as long as the ref count is above 1, they never get collected. So what can we do to fix this? Well, the key thing with this scenario is to always try to make sure to completely get rid of the native side when you're done with it. So null tells us to get rid of the managed side, right? So that's a signal that says we no longer have a live reference to it. But let's go ahead and put in here a parent view dispose, right? Dispose will actually fix a lot of memory leaks in your iOS applications. Get rid of your native handles as soon as you can by calling dispose. Let's try this again with dispose and see if that fixes our problem. So again, I'm going to add it in. I can see two references being created. I remove it. Notice that it removed my custom parent view. So custom parent view got disposed. I now have no live references to custom parent view. And when I do a GC, I can see that my child view gets disposed as well. And so dispose is actually being called by the finalizer as part of the whole destruction of that NS object graph. And so it goes through that disposable sort of pattern. And again, we cover that in detail in CSC370. So if you're not familiar with the dispose pattern, which is different than just iDisposable, there's a whole pattern that's behind it, then go and check out CSC371 for more details on that. But you can see that both of them got cleaned up. If I add another one, now there's just one live reference there. Everything is correctly being destroyed as part of the GC. Now, this is fine, and this does work, and you need to remember to do this. However, this isn't as intuitive as it could be, because really the problem is actually between these two objects. And I'm fixing the problem here in the owner of those two objects. So let's just comment this out and see if we can do something at this level to get rid of it. Now, there's a couple of things that we could do. It turns out there is an override so that when I get removed from my super view, that I can go ahead and get rid of my child as well. And so this is another way to handle this. We could go and grab this little bit of code here, drop it in here, and say if we have a child view, then let's remove it. So we'll say child view, remove from super view. That'll get rid of it from the view hierarchy, which means that we'll no longer have a retain count, and that'll drop that retain count. So let's try this and see what happens. So again, I'm going to add it in. I get both of my views. I delete it. Notice I don't see a dispose here, but I do a GC, and then I see both of them get disposed. And this is because I've successfully broken that graph, right? I no longer have the graph there. Now, here's another way we could do this. When we remove from the super view, rather than doing this remove from super view, what if we did this? Let's dispose of that child view if it exists, right? So that we're going to force dispose the child itself. Now I add them in. I remove it. Notice that now my child view gets disposed, and I do a GC, and notice that my parent view is not being correctly disposed. Okay, so just disposing the child view didn't really fix this problem. It does get rid of the native handle. However, this pointer right here is keeping it alive. And so let's go back to the parent view and let's try this. Let's say if child view not equal null, then child view parent equal null. So let's go ahead and kill our parent reference, which ultimately is really the problem we know. And let's see what happens now. So we create it, we get both of our views, we dispose it, we see our custom child view goes away. I GC, and now you can see my parent view goes away too. And so now we've sort of fixed the problem within the parent itself. But it turns out we can actually do this even better from the child. So I'm going to delete that override, and let's go look at the child view. Now ultimately, as we've sort of played with this, we can see that the problem really is this pointer to the parent view. But the thing to keep in mind here is that sometimes we don't need these pointers, these references. In fact, what if I could somehow get rid of this property, or at least the value that the property contains? So let's change this implementation, and instead of actually setting this property value, let's say return custom parent view this.superview. Remember, superview is the native reference, that int pointer that points at whatever the iOS object is. But we know it's a custom parent view. We know exactly who's adding this in. And so I can actually cast it back to my custom parent view. And at this point, I no longer have state in this object, right? I've now removed this reference here that is actually connecting those things together. And instead, I'm dynamically creating it based upon my parent view. Then what we can do is go back to our parent view here, and where we actually set that value, let's just comment that out. We no longer need that. And let's see what happens now. So I add it in, I have both of my views, I get rid of it. Notice neither one of them got disposed, but I do a collection, and I can see that my custom parent view got disposed. I do another collection, and I can see that my custom child view got disposed. So it's properly cleaning up both of those objects because we're no longer maintaining that managed tie anymore. Now, notice that it took 2 GCs to do it. There were 2 cycles there, and so if possible, you should always prefer the disposal route because that will disconnect the objects immediately. In this particular case, it had 2 full GCs before we were able to actually completely deconstruct that view graph and get rid of both of those objects. So there's another case to think about in Xamarin iOS as well, and this one actually is even a little more surprising than the one that we just looked at. And it involves delegates. Delegates are always the most troublesome part of garbage collected systems. Here's the way this problem sort of manifests itself. When you wire up a delegate event handler on a framework peer, it essentially adds some managed state to the object in the form of our delegate class. So this is one of those things that we cannot push over to the native side because there is no such thing as a delegate chain in native iOS. This is strictly a sort of a managed way of handling an event. And so therefore, what Xamarin iOS does is when we wire up a delegate, like what you see here, where we're wiring up to the touch up inside in code, it actually promotes the framework peer into a user peer. So our UI button becomes a user peer as far as Xamarin iOS is concerned. And so here's our basic example. We have a my view controller in our view did load. We've got a button that we've allocated in a storyboard, presumably. We have a name assigned to it, so therefore it creates a property that represents that button. And we wire up to the touch up inside, and notice we're wiring it up to a instance method called onProcess. And this is fairly common code. This is the sort of stuff that you would do in any sort of UI environment. But it reacts a little bit interestingly in iOS just because of the operating system architecture. And so here's sort of a look at this. Let's just break it down as to what's happening here. On the native side, the view controller itself will retain the UI button because it's in the visual tree. So we've added the button into the view state of iOS, and therefore it will bump the retain count to make sure it stays alive. We also have a property on the managed side. So the storyboard created a nice managed property to represent our button, process button in this case. And because of that, that'll also hold on to the retain count. But it turns out that it's not necessary to actually have a property to create the cycle that we're going to see here. And the view controller and the button both will have an initial retain count of 1 as part of their creation. On the managed side of the fence, the button's going to be held alive. The managed state or the framework peer will be held alive because of our process button property. And the view controller is going to get held alive because we actually have a strong reference through the event handler, the touch up inside. So if this graph kind of looks familiar, it should, because again, what we've done ultimately here is we've created another cycle reference. Right? Our view controller can't be freed because the button is holding on to it through a .NET managed reference, which keeps it alive. And the UI button won't be freed because we have a view controller that's got it in the visual tree and a managed property in the managed state that keeps the retain count greater than 1. And so ultimately we've created exactly the same cycle, but this one's a little more insidious because it's much easier to create and it's much harder to see. So how do we fix this? Well, it turns out that the way we fix this is exactly the way we fixed our delegate problem earlier. We want to make sure that anytime we wire up to an event, we always unsubscribe from it. And so in our view did appear is where we're going to move our process button touch up inside wire up. And in the view did disappear, we're going to go ahead and do a minus equal to get rid of that event handler. Now, one other thing to think about with these events is that you only have to worry about this if you manually subscribe to the event in code. If you use the storyboard to create an event handler through the actions, that goes through a different path in the runtime. Instead, that's a message notification coming from iOS that Xamarin iOS Runtime will intercept, and it will identify it through an attribute that's on your class, and it will call the method through a reflection rather than through a delegate chain. And so it means that we do not create the cycle if we're using a storyboard to wire up our event. This particular issue only occurs because of the event handler that we're actually wiring up in code. But ultimately, the solution to it is exactly the same as what we talked about earlier. Anytime you wire up an event handler for any purpose, you should always make sure there's a corresponding place where you then unwire from that event handler to ensure you don't create a reference. So let's just look at a quick example of where a framework peer gets promoted to a user peer. I have a very simple application here. It has a main view controller. This is the first one displayed. That just simply has a button in the toolbar that was created via the storyboard that does a GC collect. We also have a next button that automatically segues to a second view controller, which is defined here. Now this view controller has a slider on it, and so you can see we're using the slider value here that again was given a name in the storyboard, and we're wiring up to the value changed to actually change the value of a label that's also on the view. So let's run this just to see what happens. Notice that we do output the number of times that we've created this object, and then when we dispose it, we actually deallocate that. And so we should see that in our debug view, both the creation and the destruction of the secondary view. So here it is. This is our GC. That just forces a GC to occur. I don't have the logging turned on, and I didn't put any output into the window to say that it had been GC'd. And so we're not seeing anything. But if we go to our second view controller, we can see that it got created. There's one instance in memory. I can see that my slider is working. It's updating the value. When I go back and I do a GC, you can see that we're not seeing a disposal of that second view controller. In fact, when I run it again, you can see I now have 2 instances in memory. I run it a third time, I now have 3 instances in memory, and GC does not seem to be cleaning it up. And this is kind of a really significant issue because just looking at the code, you would not see anything significantly wrong here, right? This is the sort of code that we would write in any application that had UI things in it. So I've certainly written this sort of code in UWP apps and WPF apps, even in Android apps where I want to just use the name and I hook into an event. But it actually causes an issue here in iOS because this delegate is going to hold this whole chain alive. And again, it's simply because of the way everything sort of gets rooted in with those reference counts that are occurring. Now, what can we do to fix it? Well, there's really 2 different things we could do. The first thing we can do, and this is just what I'm going to recommend straight out, is anytime you have events that are being wired up, always make sure to unsubscribe from them. And so I'm going to create first a method on slider value changed that takes an object sender and an event args e. And I'm going to move this code that we had in that lambda into this separate method here. Then we're going to override the view did appear, and let's wire up to our event inside our view did appear. Now I'm moving it to a method simply so that I have access to this method body later to be able to unsubscribe. And so we'll say this is on slider value changed. And then in the override view did disappear, let's do the same thing but unsubscribe from it. So we'll say minus equal, and let's run it again. And let's see what sort of effect that has on our structure here. So the app launches, I create a new view controller, I see there's 1 of them. This is still working, that looks good. Now I GC, and notice now I see that my view controller gets disposed, because now I'm unhooking that event, and therefore it's not going to keep that chain alive anymore. So that's the first thing that we could do. We could actually just simply make sure to always unsubscribe from the event somewhere, and just in order to make it a pair, that means I move it into my view did appear. Here's the second way we could do this. I'm going to comment both of these out, and instead I'm going to go into the storyboard. And here in our storyboard, I'm going to take this second screen here, and rather than wiring up to the slider via the name, the identity here that we've created, I'm going to go to the Events tab, And I'm going to go ahead and pick the value changed here, and let's just say on slider value changed, and hit enter. It'll then let me create a new method. Now I can't share the existing method because notice the signature is different. And so I'm just going to go ahead and move this code in here, and we'll just delete the other one. And now what we've done is we've actually handled the event through a message notification coming from iOS. And it turns out that if you do it that way, we don't have this problem because there's no delegate chain involved in that approach. So I create my new view controller. I can see that I can still slide. It still works. I come back and I do a GC, and you can see that it is getting disposed properly. And so either approach will work. Either use the designer in order to wire up the actions to methods that are in your view controller, or make sure to always unwire from your delegates if you wire them up in code. So we've covered a lot of ground, and we've looked at several specific cases in Xamarin iOS that you need to watch out for. Here's just a couple of tips to think through as you sort of process this material. The first tip is always prefer full delegate methods over lambdas. Lambdas ultimately turn into regular delegate methods, but they often end up holding on to references that you can't see just because of the structure of the lambda. It's a lot easier to see delegate references when you actually create methods in your class, and so you can really see the relationships between them. Always make sure to call dispose on any of your native resources to clean them up when necessary. And so it's not necessary to do that with view controllers and things like that. The system will automatically get rid of those, assuming we don't create the cycles that you've seen here. But if you've got things like UI images and big objects that you want to get rid of independent of the GC, remember that all of our native peers always implement iDisposable, and you can call dispose to get rid of those native handles. And then finally, just good advice generally speaking, always unwire or unsubscribe from events that you wire up in code. This will always create some sort of cycle and invariably leads to a memory leak. And so look for places in your code where you're wiring up to an event and not unsubscribing from it, and make sure that you have the corresponding unsubscribe. So let's switch gears and let's talk a little bit about how Android manages memory, because it's actually different than Xamarin iOS, and the model used is quite different than Xamarin iOS. So to start with, just like we did with iOS, let's talk about how we manage memory in a Xamarin Android application. First of all, recognize that Android also has a garbage collector in the system. So unlike iOS, Android is not a reference counted system. It is a GC-based system, just like .NET. Now, this means that we have added a little bit of complexity into our world, because now we're going to have two different garbage collectors actively trying to keep our app clean. And it means that these two collectors have to be synchronized, and they have to work together, or our application is going to have serious problems. So let's look at how this works from a Xamarin Android perspective. First, Xamarin Android also creates peer objects. And so again, these are simply wrappers that represent the native objects that were created. And by native in this sense, I mean Java-based objects. And so recognize that the majority of things that you'll interact with in Android are really things that are owned and created by the JVM, the Java Virtual Machine. They're Java objects that have state in the JVM. And we create peer objects in the mono runtime that represent those Java objects. And so essentially we have an int pointer, just like we did in iOS, that represents an actual reference to the object in the Java world. And we use the Java native interop to be able to communicate with the JVM and kind of interact with it. So this is all encapsulated in an interface called iJavaObject. And notice iJavaObject is iDisposable. Just like NSObject in the iOS world, we can dispose of any of our Java objects, and that will in turn free the handle that represents the native Java object. So if you want to disconnect the peer from the native handle, you can always call dispose on it in order to force the system to release that handle early prior to the garbage collect kicking in. When you allocate a peer object in the mono world, the system captures the underlying native Java object and it holds it in that int pointer. And as far as the JVM is concerned, it treats our reference to it as a root. In other words, as long as our managed Xamarin object lives, the Java object is considered rooted and it will not be collected. And so just like in iOS, both sides have to agree that this object is ready to be collected before we can actually get rid of the memory. Now, again, just like we saw in iOS, part of the object state is actually on the JVM side, where we actually have all of our Java things, and some of our object state may be on the Xamarin side. And so we're going to split the state between these two worlds based upon how we construct our object. So let's look at how the garbage collection system has to work in order to make all of this function properly, because it is a little bit different than the normal GC process. First, GC at some point is going to kick in our application, and it's going to run just like it normally does. It's going to identify all your roots, and it's going to decide what's alive, and then it takes some special steps. First, it looks at every object, and it decides, is this a peer object? And if it's not a peer object, then it just goes through the normal collection cycle and it collects the object as normal. So the object's not reachable from our code and it doesn't represent a Java thing, so it just falls into the normal managed GC system. But if it is a peer object, if it represents something that's in the JVM, then it goes into that object and it replaces the JNI handle, the int pointer, with a weak handle. A weak handle in Java is exactly like a weak reference in .NET. It represents something that will not keep the object from being collected. It gives us a handle to the object, but it's not a strong handle, it's a weak handle, and the garbage collector on the JVM side can collect the object if necessary. It'll do this for all the objects, then it will force an Android GC. This will then cause the GC system on the JVM side to go and collect anything that is collectible on their side. And keep in mind that because we've replaced all of our JNI handles with weak handles, our managed side in the Xamarin world will not keep the Java objects alive anymore. So they're no longer strong handles, we will not root them, and the JVM will go through and it will say, okay, anything that I can't reference, we're going to go ahead and collect. At the end of that, we'll catch, after the JVM has done its collect, we'll catch that notification, and it will look at every single one of those objects and it will say, has this object been collected by the JVM? In other words, is it still alive from the weak handle? If it's not alive anymore, then we go ahead and collect our managed peer object. And so the memory on the Xamarin Android side will then be collected and it will go away. However, if the object is still alive in the JVM, then we're going to turn that weak handle back into a strong handle reference, and we keep the object alive for another garbage collection. And so we'll just keep running at that point, and then the next time we do a GC, we'll go back through this process again. Now keep in mind that we're simplifying the view of this a little bit. In other words, there are a few more steps that are introduced as part of the bridging process between the Xamarin garbage collection and the JVM garbage collection. But this, in general, is the big picture of how it's all going to work. And so each collection is going to have to go through this process of identifying Java objects that are no longer alive and then collecting them on our side. So because Java has a garbage collected system that's going to happen here on our Android apps, it turns out that we don't have the same reference cycle problem that we saw in Xamarin iOS. And so where we created these user peers that have state that cause the object to be rooted on our side that keep it alive in the native side, that's not going to happen here. Garbage collected systems are incredibly efficient at identifying managed cycles like that. And the same is going to be true here. You won't be able to easily create that sort of cycle in this sort of environment. However, there are two things that are going to happen as a result of having these two competing GC engines. The first is that our garbage collections are going to take longer. Every GC that we do in Xamarin is going to require more work to identify and interact and synchronize with the Android GC. I mean, even just looking at that graph that you saw earlier, you probably intuited some of that. There are more steps that are necessary. We have to wait for the Android GC to occur, which means that the process of actually doing a garbage collection means our application is going to be paused longer during the GC itself. The second consequence of this is that the memory pressure is typically going to be higher. Now, this is a common problem with most GC-based applications. Memory is delay-freed. We don't free it immediately when we're done with it. Instead, something else comes along and identifies the free things and frees them up at a later point in time. It's not deterministic. And adding a second GC into the system just makes that problem even more pronounced. Now, normally, GC runs when an allocation fails, and that's certainly going to be true of this platform as well. But we also maintain some special heuristics that watch memory pressure, and when memory pressure hits certain thresholds, will automatically run GCs even if an allocation has not failed. And so the system will automatically just monitor the working set of the process and then run GCs on its own to try to make sure that we don't run into an out-of-memory condition when we don't expect it. So with these two disadvantages to our model in mind, let's talk about what we can do to kind of minimize the effect on our application itself. So the first sort of thing that we can do to improve our GC performance in Xamarin Android is we can reduce our working set by releasing objects as soon as we're done with them. Now, this is good advice regardless of whether or not it's Xamarin Android, .NET, ASP.NET, Xamarin iOS, but it's particularly relevant to Xamarin Android just because a lot of times our memory pressure tends to be a little bit higher in the Xamarin Android world, and we tend to run on devices that don't necessarily have as much memory as we're used to on other platforms. So Xamarin Android runs on very low-end hardware devices, and so memory pressure becomes a key factor to how well your app performs. So here you can see that we're allocating a bitmap and a drawable to fill in a view background, and we're going to use the using statement here to ensure that we call dispose on both of these objects. And what this is going to do is it's going to release the native resource on the JVM side. And it's going to disconnect the peer that's represented by our managed Xamarin Android object from the JVM object that was allocated in Java. And that way the two GCs can act independently. In other words, collecting one side is not dependent upon collecting the other side. And so this is relatively important, particularly for large objects, such as images, where we may have a lot of memory committed to it on the native side of the fence that we just simply can't see on our side. A second advantage to ensuring that we dispose these objects is because they are disconnected, it means that the Xamarin GC will run a little bit faster, because there will be no Java handle associated with the object, and therefore it's not considered a peer anymore. And so when we do the GC process and it looks at the object and says, is this a peer? The answer will be no, because there is no object allocated for it. And so it'll just go through the normal GC semantics because it's no longer connected to the Java side. Now, in addition, if we've got some static values, so notice we have a static byte buffer up there, or perhaps we have some class level fields or properties, you can set these to null when you don't need those values anymore. And it allows the GC to reclaim these objects and release the memory. And so here we've got a static buffer that we're reusing that holds our dynamically created image. And once we're done with the raw bitmap class, or the raw data that we pulled in, we don't need that buffer anymore. And so we can set that buffer to null. Now, keep in mind that generally speaking, there's no need to set method variables to null. Those are tracked by the JIT compiler, and they'll get released at the end of the method. And so as soon as our method is done, methods that are allocated midstream inside of a method that are only used inside of a method, more often than not, there's really not an optimization to be gained by releasing those unless they're really large, in which case it's better to just dispose them and get rid of the native side and then let the GC pick up the small object on the backside once the method is finished. This advice, as I said, is particularly important for large objects. Things like images are good examples of this. So notice here, in this case, our peer object is going to be about 20 bytes in size. That's about the size of an object that's been allocated in mono along with the state of an int pointer to point to the native thing. But the actual memory that backs the image itself is going to be a lot bigger because it's going to represent all the bits to color the image. And so in this case, you can see that on disk, this image is about 479K, but once it expands, because most image formats are compressed, it's not held in a compressed format in memory. It's fully expanded out to whatever the bit pixels are. It's going to be about 1.5 megabytes in size. That's a pretty significant chunk for a low-end Android device. And so getting rid of this object as early as possible is going to be crucial to trying to make sure that our application continues to respond appropriately. Now, .NET includes some APIs that help with this, like GC add memory pressure. However, these methods are not implemented in mono, and so they don't work in our Xamarin Android or Xamarin iOS applications. And as a result, the only real thing that you can do here is dispose these objects so that we free up the native handle as soon as possible. Another technique that we can use, and this is particularly relevant to Xamarin Android, is to periodically trigger GC. Now, I know a lot of you are saying, we've been told never to do that. And that's true. That's good advice. Let the GC do what it's supposed to do. But again, because of our unique sort of presence in the Xamarin Android world with these low-end devices that don't have a lot of memory, it can be helpful in certain circumstances to force a GC to occur. Now, what are those circumstances? Well, here's one here. I'm loading a bitmap from a stream that comes down from a network client. And I'm going to use that bitmap and do something with it. And once I'm done with the bitmap, I'm going to throw it away. I know that it was a big block of memory that I just pulled down from the stream. We allocated a bunch of bytes to hold the memory stream. We allocated a bunch of objects to create the bitmap in memory. All of those things need to eventually be collected. If I know that I'm done with those objects right here, and I've released them all, and I'm not holding live references, I can force a GC to occur at this point and make sure that we clean them up. Because the key thing is with GC, we want to make sure to try to clean things up as early as possible, specifically when objects are still in the nursery. It's a lot less expensive to clean them up in the nursery than it is if they get promoted to the major generation. And so if you're interested in this particular technique, make sure to go watch XAM370 because we give you some practical examples of this exact scenario of watching out for midlife promotions of objects. So keep this technique in mind. If you've allocated a bunch of things in the context of a method, after you're done with that method, it can be useful to call GC collect to force those things to be collected. In addition, it can be useful to actually call GC collect before we call this load bitmap to make sure that all the allocations occur in the nursery so that they're in the nursery when we do the next collect and therefore they get cleaned up a little bit easier. So let's talk about trying to minimize the work that's done by the GC itself. One of these special cases that you're going to hit in Xamarin Android is the additional work that you saw that it has to do with your user peers. And so let's look at a common example of that. Here we've got an activity which is holding onto a list of C# objects that represent tweets. And we've got up to 1,000 of them inside of our list. And in our onCreate method, notice that we're creating an array adapter to display these tweets. Now, when the GC system runs, it's going to identify pure objects that are held by the system. And remember that these are objects that ultimately represent some Java thing, such as our feed activity here. And so because feed activity derives from list activity is a Java thing, and therefore feed activity becomes a user peer that we're going to work with. And we saw that the GC has to take some special steps to clean these objects up because it has to actually interact with the JVM's GC in order to properly get rid of the memory that's associated with this. However, we skipped one of the steps that the system actually does, which is what's called a relationship walk. It turns out that the Xamarin Android GC looks at all the fields of any peer types that it encounters. And so that would include this feed activity here. And it walks the object graph for each one of those instances to determine if any of them point to other peer objects. And so in this case, we're going to see that there's a list of tweets inside of our feed activity. And inside that list of tweets is going to be an array holding on to tweet objects. And it's going to walk that array and look at every single object inside that array to see if any of them are in turn peer objects. And so this walk has to be done on every single GC that we do. And it might seem like it's no big deal. And it turns out 99% of the time, it's not a big deal. It really doesn't add a huge expense to the GC walk. It's just an additional step that needs to happen. However, when you have a large object graph that's held onto by a user peer, it can add some expense to the GC process that has to occur here. So let's take an example. What if each of our tweets had a bunch of objects in itself? And so notice here we've got an ID, some text, some more retweets, which has tweets in themselves. We've got another string to create it. We got some hashtags, which is a list of string. We have an in reply to, which is a string, a language, which is a string, and a location, which is a place object. Now, every time the GC runs, it's going to walk through that list, which is going to walk through the array, which is then going to walk through every one of these objects and look at every reference type in it. And it's going to look at each one of these little references and it's going to say, is this a peer? Is this a peer? Is this a peer? And that may seem like no big deal, but the more objects we add into this and the more complex those object graphs are, the longer that relationship walk is going to take, and it's going to start impacting our GC performance. And that's important because remember, while the system is doing the GC, it's not doing anything else. So our application is frozen in time until the GC completes. So Xamarin Android and Xamarin iOS both have what's called a stop the world collector. We don't do concurrent collections. The application literally stops every thread while we do a collect. And so you might be asking, why in the world does it have to do this relationship walk? Because it seems a little bit inefficient. Well, let's look at an example of why. And this may help you to understand exactly why we have to do this relationship walk. Consider here a custom C# class named bitmap button. And the purpose of this is to hold on to an image that we're going to display inside that button. And so it has a field to the managed peer instance, right? We've got some kind of field that represents the bitmap itself. And of course, we have our endpointer handle to the Java button itself. And we've got the button inside the visual tree. The bitmap has a handle to some Java bitmap, right? And so you can sort of see the relationship that's been set up here. We've got a managed C# relationship between the bitmap button and the bitmap. And we have a unmanaged relationship from the bitmap button to the Java button and from the bitmap to the Java bitmap. Now remember, when the Xamarin GC runs, it's going to look at that bitmap button and it's going to recognize that it's a peer and that it's not reachable in our C# code, right? So in other words, we no longer have a reference to the bitmap button. And so it's going to replace the handle in the bitmap button with a weak reference. And it's going to run the GC on the Android side to see if it's dead to Java. And if it is, we'll collect it. Now, Android's going to look at that bitmap button and it's going to say, nope, I can still reach that because it's in the visual tree. So the handle's still alive. Therefore, we're going to keep the Java button around. However, it's going to look at the Java bitmap and it's going to recognize there are no live references to this bitmap. Remember, we replaced the bitmap's handle with a weak handle. Therefore, our managed representation will not keep that bitmap alive, and Java will collect that bitmap. Now, the question is if Java collects that bitmap because we don't have any references, then what happens to our application, right? That potentially could be really, really bad. And so we scan for relationships to ensure that each one is mirrored on both sides. And so when we actually set up this bitmap button to bitmap relationship, when the GC runs as part of that relationship walk, the system will inject, using some Java interop code, a native reference between the Java button and the Java bitmap. And so it'll essentially mirror the managed relationship, but it'll do it on the Java side. This ensures that when we run the Java collection, and we've essentially set up both of our handles to be weak references, the system will see that the Java button can't be collected because of the visual tree, and it will see that the Java bitmap can't be collected because of the Java button. And that way, when we return back to our C# side, all those relationships will still be in place, and we won't have collected things prematurely. This just ensures the stability and integrity of our system. Now, back to what we just talked about in terms of our feed activity. It means that when we hit that list of tweets, we have to walk every single one of those tweets looking for those peers, even though none of them are peers. And it could be that there are some optimizations that could be performed there. For example, we could look at that list and say, well, we can see that it's a tweet and it doesn't derive from Java objects. Therefore, we know about list There's no need to walk any of those objects because none of them derive from, or none of them implement our iJava object interface. However, that's an optimization that's not completely there today, and so it does actually walk every one of those objects, which means we should be thinking about that. Now, there's a couple of things that we can do in order to sort of improve the performance of the Java walk. Here's one example. We can move the tweet data into another class. In other words, notice here we're moving tweet data to a static class. The static class is a managed class all by itself, and so it's what's going to hold on to our list of tweets. In our feed activity, we reference that static class. And so we go to our tweet data and we say, give us all the objects from the static class. Notice in this case, we do not have a direct live reference to it as a field of our feed activity. That's the key. What the system's going to look at are all the fields and properties that are on the object itself, on the peer, and those are what it's going to scan, the relationships that it can get to. It's not looking at code, it's looking at the relationships that are contained within the instance. We've now broken that relationship. It's still implicitly there because we're using the tweet data as part of our static class that's feeding the array activity, but it's not there as far as the GC is concerned. And so that means that our tweet data can be collected independently of the feed activity. We've removed the need to do the relationship walk. Keep in mind that we're talking about significant object graphs here. And what that means is if you see that you've got a very large object graph that you recognize is holding on to objects that have a lot of other references, that's where you're going to want to do this sort of optimization. 99% of the time, that's not going to be the case. And so if you just have a couple of fields in your activities, or any of your Java objects for that matter, that are just strings and little things like that, or even pointers to objects that just have a couple of strings in them, that's no big deal. I would not bother to do this sort of optimization for those types of constructs. What we're talking about here is where you're holding on to a reference or a set of references that in turn hold on to a lot of other references. That's where you should be looking at potentially breaking those reference graphs into something like this in order to help the GC out. Now, there's a second application here as well. And this is another interesting issue that's in the code that we just looked at. So it's the use of this array adapter of tweet. So it turns out array adapter is actually a peer object. Array adapter is a class that's on the Java side, and it's implemented completely in Java. We've just simply wrapped it in a little wrapper on the C# side. And the fact that we're using this Java object actually introduces a bit of a hidden problem here. And so let me show it to you in a more graphical way to help you understand exactly what's happening here. So notice that we've got a class tweet that's just a C# object, and then we're using array adapter of tweet in order to feed our list adapter. And the way this is really going to get constructed in memory is we've got this array adapter. Array adapter holds onto an array list in Java that has a bunch of pointers to it. Those pointers point to tweet objects that are really just little Java objects that were created to represent the tweets that we're holding in the array adapter. And the reality is, what's going to happen here is the system is going to have to essentially box all of our objects that we're passing into array adapter and create little mini representations of them that are pointers to the real managed objects on the Xamarin side to represent them. Right? And it's just going to pull strings out of them. So it'll essentially just do a toString on every single one of these objects. So that's the purpose of these little managed objects, is so that Java can call toString on it, and that'll get forwarded to the tweet that will then return a string that comes back to the Java object that then gets represented in our list view. However, this can get quite expensive for a couple of reasons, because the objects are going to take up more space, because now we've got representation in both the Java side and the .NET side. The GCs are going to take longer, right? Because now we've got to follow all these links, and both GCs have to be involved whenever we do any cleanup. And there's a cost to going back and forth between our Java platform and our .NET platform, right? So it's preferable to sit as much as we can on one side or the other. Ideally, we want to minimize this. And so that's one of the reasons why if you go through the Android 110 class, one of the things they'll tell you is don't use array adapter for anything except very, very small lists. And so if you've got 100 items or less, array adapter probably won't matter at all. Once you start going beyond that, it requires a lot of scrolling. On low-end devices, array adapter can cause performance issues. How we fix this is we don't use array adapter. Instead, we create our own custom adapter that keeps us in the managed C# world as much as we can. So in this case, we're going to derive a class from base adapter of tweet. Now, again, base adapter of tweet is a Java thing, or at least ultimately it will end up being a Java thing that implements some Java interfaces. But we're going to move some of our code or processing code into the C# side so that we'll spend more time there and we'll allocate all of our memory there. Now, ultimately, what this is going to end up with here, where we use a base adapter, is we're going to have a graphical picture that looks somewhat like this. Notice now we have our tweet adapter that implements an interface. That interface is going to feed the list view, and so it's still going to end up bouncing back and forth between the two worlds. We really just can't avoid much of that. But the actual memory allocations are going to be significantly less on the Java side. We're not going to be allocating a whole bunch of Java objects to represent our tweets. Instead, that's all going to be sort of contained within our C# code that represents the adapter, and then we're just going to feed the strings over to the list view in order to populate the data. So this turns out to be more efficient for large lists of data that are populating our list views. And generally speaking, you should follow this approach regardless. So even for small lists, I would advocate using a base adapter over an array adapter. They're just a lot more functional. You can do more with them. You can have different presentations of data. There's a lot of reasons to use your own custom adapters over the built-in array adapter. So the last thing that I want to look at with Xamarin Android is some specific code which actually sort of interops between the Xamarin garbage collection and the Android garbage collection. So we've got a little piece of code that's sort of custom in Xamarin Android called the GC bridge. The GC bridge is the piece of code that's responsible for actually doing all the messaging between these two memory management systems. And so all of that work that we saw in the graphs where we said, is this a peer object? Go ahead and issue the Android GC. Go ahead and look and see if the object's been collected. All of that work happens in the GC bridge itself. And so this actually is compiled as part of the garbage collection system itself. So when we build Xamarin Android, this is a component that gets kind of stuck into the GC, and the GC has hooks to be able to kind of call out to the bridge and give it an opportunity to do its work. And ultimately what the bridge accomplishes for us is it allows us to sort of be able to hold references to Java objects and have Java objects hold references to C# objects, and it kind of manages all that work of collecting both of those worlds. And so as you can imagine, it's kind of a complex bit of code. And because of that complexity, the bridge process itself can be a little bit expensive, and it can cause noticeable performance differences in your application. Now, you can get a sense of how expensive the bridge is by looking at the Android debug log. So as I said earlier, Xamarin Android outputs GC messages into the log debug build, and it reports how long each GC takes and how much time of that GC the bridge was responsible for. There are also some unique GC bridge messages that you'll see as well that provide some internal details for the Mono development team, and you'll see them in the output, but there isn't a lot of in-developer useful data in those messages. Really, the main detail you'll get out of the GC bridge messages is which GC bridge implementation is actually being used. And it turns out that we have a couple of different GC bridge implementations that we can utilize in our applications. We can actually change that implementation by providing an environment variable in Android to tell it on startup which one to load. So there are 3 different bridge implementations that are supplied with Xamarin Android. First, we have the default bridge implementation. This is named old. This is the most tested and trusted implementation, and it's been around a long time. And if you're happy with the GC times that your application is getting, then you should just stick with the default bridge implementation. There's no need to change. The second bridge that we have is the new bridge. This is a rewrite of the old bridge. It uses exactly the same algorithm, but it improves the performance of some of the edge cases that we run across. This is considered stable, but it's not mature enough to be the default bridge for all cases. And in fact, when you're changing the bridge, a key piece of advice is make sure to profile your app and test every single scenario. The third bridge implementation we have is the Targin bridge. This is a completely different algorithm based on Robert Targin's strongly connected components graph algorithm that he worked on at Princeton. This algorithm tends to perform the best, particularly under load, when a lot of objects are connected together. But it's also the most experimental, and it hasn't been tested as thoroughly as the other two because it hasn't been around the longest. To give you some idea of the performance differences, here are 2 common app scenarios in graph form showing the GC collection time in seconds. The first graph is a test that creates the objects and randomly connects them together, which sort of simulates deep object models that we see in some applications. And here you can see that as the number of connected objects increases, the time to collect them goes up exponentially in the old bridge mode, but remains somewhat consistent in the other 2 bridges. The second graph simulates the case where a very popular object is referenced by many objects. And this can happen when the GUI has lots of callbacks to some central backend object. And as you can see here, it's not just faster, but it's also more scalable as the number of incoming links increases. You can see that it barely affects the performance of the GC time. So if you'd like to change the bridge implementation just to try one of these other bridges out, you can do that by setting an Android environment variable. And we do that through an Android environment text file. So all you need to do is add an environment text file to your project. This is just a regular text file, it can have any file name. The key is that the build action has to be set to Android environment. The text inside the text file is a single line per environment variable. And notice that the variable that we want to set here is mono_gc_params in all capital letters equals bridge-implementation equal, and then you specify one of 3 values, old, new, or Targin. This has to be set up inside your application. Then when your app runs, it will load that appropriate implementation as the bridge, and you'll see that the output in the log file will change to indicate which bridge is being used. Now, I can't stress this enough. The new and the target bridges are considered experimental code. And so if you decide to change the bridge implementation, you must test every aspect of your code. And what you'll likely find is that it may have no impact on your code. It may even worsen the GC performance of your code. It might even cause memory leaks in your code because it's not picking up all the graphs. Right? So it's not been tested for every single sort of scenario. The old bridge is very thoroughly tested. It's been around a very long time. And so bottom line is, make sure to test your app. There are some apps that will do a lot better with a newer bridge implementation. There are some apps that won't. And so it's just on an app-by-app basis, you're going to have to look at it and see what sort of impact it makes on your particular application time. So now we've sort of walked through all the Android sides of the fence, and you've seen a few memory issues that can occur in Android, although recognize that the subtle issues that we saw in Xamarin iOS really just don't occur in this environment. But there are some tips to think about as we sort of close out the Xamarin Android discussion. First, make sure to call dispose to release native resources immediately as much as you can. This is particularly important in Android where we want to sort of disconnect the two GC systems from each other. As you saw, you should avoid placing large numbers of references on peer objects because it affects the relationship walk that we have to do. Again, remember, you only have to worry about that if it's a large object graph that potentially affects performance. Small numbers of objects on your peer objects are fine. There's no need to separate them if it's just a handful of things. Beware of Java interop scenarios where you're using Java objects like array adapter, but passing in a bunch of C# objects that have to be boxed into Java objects to be used. And then finally, you can look at the GC bridge options to see if it has any impact upon your application. Now, one last thing. A lot of people wonder about Xamarin Forms and how much of this advice actually applies to Xamarin Forms. The answer is not a lot of it. So Xamarin Forms actually adopts all of the principles that we've talked about in this particular class. So the framework renderers that are used on iOS and Android all manage disposing for you. They all properly deal with reference cycles and things like that. And so we've got a lot of unit tests in Xamarin Forms to ensure that it properly manages memory the way we expect it to. And what that means is that when you're using Xamarin Forms itself and you're just using the objects that are present in the Xamarin Forms framework, you won't have to worry about any of this. Now, can you create memory leaks? Of course you can. You can still create delegate references, and you can still have lists of objects that are holding strong references to things that cause them to not be collected, just like we talked about in the very beginning part of this module. But generally speaking, the platform-specific problems that we've covered here are not going to happen in Xamarin Forms. Now, where they will happen is when you're dealing with custom renders or effects. And so if you're actually integrating more deeply with the platform and you're starting to provide your own native representations of objects, particularly visual objects, then you will have to follow all the rules that we've talked about. And so you'll want to make sure not to create reference cycles in iOS. You'll want to make sure to dispose of things properly in Android. All the sorts of little caveats that we've sort of discussed on an iOS and Android basis, you'll want to follow whenever you're doing any sort of native UI work, even when it's inside Xamarin Forms. And so just be aware that Forms will take care of it as far as its own objects is concerned, but it won't protect you once you start diving into the native platform on your own. So thank you so much for attending this particular class on diagnosing memory issues in Xamarin iOS and Xamarin Android. I hope this class has been helpful to you. If you have any questions, feel free to email me at smmark@microsoft.com. Or, of course, you can post your questions to the forums where we'd be happy to interact with you. Thank you again for attending this lecture and for being a Xamarin University subscriber.